Yeah, and then now I'll hand over to Ziquan, and he will talk about the results that we have. So Ziquan, take it over.
Hello, everyone. My name is Ziquan Lin. I'm currently a master's student in Hong Yi's lab. First of all, I would like to introduce Mel Hubert, a more efficient version of Hubert. Next page. In this feature, we have Hubert on the left and two variants of Mel Hubert on the right. The main difference between Hubert and Mel Hubert is that we remove the convolutional feature extractor in Hubert and let the model directly take log Mel feature as input. The ConvNet actually account for 33% math in Hubert, which is a huge computational overhead. However, log Mel features have a frame period of 10 milliseconds and does not match the 20 millisecond frame period that Hubert has. This means that the input sequence to Mel Hubert is 2 times longer than to Hubert. So we train a variant of Mel Hubert called Mel Hubert 20 millisecond. For Mel Hubert 20 millisecond, we downsample the input log Mel feature by half to match the frame period of Hubert. Next page. We follow the two-stage training of Hubert. We predict the cluster IDs of log Mel feature in the first stage and predict the cluster IDs of the 8 hidden layer of the first model in second stage. Next page. Here we show the multiply accumulate operations or max of Mel Hubert, distill Hubert, and the original Hubert. Lower max usually means faster in runtime, but depending on how the operation are parallelized, this is not always the case. Although Mel Hubert ends up having more max compared to Hubert due to the difference in sequence length, Mel Hubert 20 millisecond has significant fewer max compared to Hubert. Next page. In terms of phone recognition, Mel Hubert is now far behind Hubert. However, there is still a gap between Mel Hubert and Hubert on speaker identification. It might be due to the absence of ConvNet, and we are currently looking into this. Next page. That is our baseline model, and let's move on to weight pruning. In weight pruning, we iteratively prune some percentage of weight in Mel Hubert followed by fine-tuning until the desired sparsity is reached. Next page. This figure shows the pre-training loss of iterative weight pruning. The red dashed line represents the pre-training loss of Mel Hubert. The spikes in the figure are the places we do pruning. The pre-training loss can be maintained up to a certain point and eventually goes up. Next page. In this figure, we show the result of weight pruning. Dense models are on the left, while sparse models are on the right. The loss is maintained up to a density of 60%. For the downstream task, we can prune nearly 50% of the network without any performance drop on phone recognition and speaker identification. Sometimes we even get better performance along the course of pruning. In the limit, we can achieve a density of 8% with only 2% drop in phone recognition and 5.5% drop in speaker identification. Next page. This GIF shows how the weights are pruned across layers. The blue line is the average density of the entire model. In terms of the layers, the first, the second, and the last layer are pruned the most. In terms of individual metrics, the value metrics of the multi-head attention and the FC layer right after are pruned more than the query and key metrics. Next page. Let's now move on to head pruning. There are several approaches to head pruning. The first one is prune based on L1 known of the weight or the L1 known of the gradient. The second one is to skip ahead when the attention map is sufficiently diagonal. When the attention map is sufficiently diagonal, we approximate it with an identity matrix and implement it as a skip connection. Next page. This figure shows the training loss of the first approach. Pruning based on the weight is shown in blue, and pruning based on gradient is shown in green. We explore different pruning schedules, and that is why the other green curve is so much to the right. We find that pruning based on gradient maintains a better loss than the one based on weight, but it requires a data set to compute the gradient. Next page. In terms of the downstream performance, again, dense models are on the left, while sparse models are on the right. All approaches are effective up to a density of 50%. That's what we have already observed in the result of weight pruning. Sometimes the performance will improve when we prune. We also know that achieving a lower loss does not necessarily imply that the downstream performance will be good. The two correlate well with each other most of the time. Next page. This GIF shows how the heads are pruned over time with the gradient. We could see that there are more diagonal attention maps in the middle layers. The diagonal attention maps are also more likely to survive during pruning. Next page. It is now a good time to talk about the skip ahead approach, as it tries to approximate diagonal attention map with identity matches. The pink line in this figure is loss curve for the skip ahead approach. We see that the spikes are much higher than others. The model after pruning struggled to maintain low loss. Skipping diagonal attention has since overall harmful to pre-training. Next page. For the downstream performance, skipping diagonal heads breaks the model ability to do phone recognitions. This shows the diagonal attention heads are important for both pre-training and the downstream task. We do have some further analysis on this. Please feel free to ask questions during the Q&A. Next page. Let's move on to low-rank approximation. If we look at this figure, recall that there are two FC layers in a transformer layer. The middle dimension 3072 is particularly large. To reduce this dimension, we prune the columns of FC1 and the rows of FC2. Similar to wedge pruning and head pruning, we use L1 norm of the weight to decide which columns and rows to prune. Next page. As a sanity check, we compute the singular values of the FC1 and FC2 layer. And here we show the singular values of each individual layer. We can see that the singular values drop quickly for most of the layers, meaning that they are inherently low rank. Next page. This slide shows the training loss of pruning the FC layers. The red line represents the pre-training loss of male puber. Similar to others, we can maintain the loss values for several iterations. Next page. Here is the downstream performance of pruning the FC layers. We get only 1% performance drop in phone recognition and less than 1% performance drop in speaker identification up to a density of 50%. Next page. The last compression technique we will look at is knowledge distillation. We train a smaller student male puber against the regular male puber by minimizing the KO divergence of their output probability distributions. We have two settings, one with the regular mask reconstruction, except that the target is measured by the KO divergence, and another without masking the input. Next page. This slide shows the downstream performance of knowledge distillation. The blue bars are the 2-layer student models, and the green bars are the 6-layer student models. A darker color means we use masking during knowledge distillation, while a lighter colors mean we do not apply masking. It is clear that the 6-layer models perform better than the 2-layer ones. In fact, the speaker identification performance is fully recovered by the 6-layer models. There is still a gap to recover the performance on phone recognition. Overall, depth seems to be important for knowledge distillation to work. This completes all the model compression technique. I will hand over to Yan for sequence compression.
Hi, everyone. I'm Evain from National Taiwan University, and now I'll talk about sequence compression. Next page. While there are many works focusing on compressing the model architecture, reducing the sequence length can also effectively reduce the computational cost. For example, the transform layer has quadratic complexity in the length of the input sequence. So by reducing the sequence length, there would be a significant speed up in computation, and the memory footprints can also be reduced. Also, subsampling in SSL is less studied. So here we present a study on the impact of subsampling on different downstream tasks, and we also explore the limit of the compressed rate. Next, please. And here is our framework. To push the boundary of small yet competitive self-supervised speech models, our work is a combination of knowledge distillation and sequence compression. The model architecture and the pre-training pipeline is based on the work Distill-Hubert. We propose adding a subsample layer inside the model architecture. And we add this subsample layer right after the CNN feature extractor so that we can reduce the computational cost of the transformer layers. And we have two ways to incorporate this subsampling inside the original pre-training framework. The first is that we subsample and then upsample our model's representation so that we can directly compute the loss with the original SSL target. An alternative way is that we subsample both the model's representations and the target with the same subsample method. Based on some of our preliminary results, we found that subsampling the target achieves a better overall performance while having less computation. So we will just focus on this subsampling target setting in our later experiments. Next, please. Next. We explore two types of subsampling, fixed length and variable length subsampling. The fixed length subsampling is a naive approach, typically using a convolution layer or mean pooling. So the fixed length subsampling serves as a baseline for our proposed variable length subsampling. And for our fixed length subsampling baseline, we simply apply an average pooling layer on both the student and the teacher model. And the subsampling rate is controlled by changing the pooling stride. Next, please. The variable length subsampling involves finding a segmentation. Our approach is inspired by this work, continuous integrate and fire, CIF in short. Briefly speaking, the entire operation is that first we have the hidden vectors after the feature extractor. And there will be a small alpha module producing a sequence of weights alpha that falls between 0 and 1. And the CIF function fires an output whenever the accumulated sum of alpha up to time t reaches a firing threshold. So for example, in this figure, if the threshold is set to 1, then there would be a boundary located at the second and the fourth time step. The CIF function then does something very similar to weighted sum, producing an integrated representation according to alpha weights within each segment. And note that in order to compute the reconstruction loss, we need the output length of the student and the teacher to be exactly the same. And in this variable length subsampling case, this is realized by having the student and the teacher share the same set of alpha weights generated by the student. Next, please. And in the case that if we have access to some pre-extracted boundaries, a guidance loss can be added on top of the original SSL loss to guide the alpha module's prediction to learn more meaningful boundaries. So for example, if we have some unsupervised SSL codes, the boundaries are obtained by the repetition in the codes. And then we generate weights for supervision based on the boundaries, having equal weights within each segment. And with the supervision weights, we minimize a frame-based and a segment-based loss between the supervision weights and the weights generated by the alpha module. For the unsupervised boundaries, we explore Hubert codes and the unsupervised ASR codes. And we also tested the effect using force alignment as our segmentation guidance. Next, please. And here are the results. As we can see, phone recognition is pretty much affected by the sampling rate. Since with shorter sequence, performing alignment becomes more challenging. For phone recognition, compressing the sequence to a frame period of 40 milliseconds, which is approximately half the length of the original sequence, the performance did not drop at all. But when further compressing the sequence, as the sequence length gets closer to the phone label length, the performance starts to get affected. we can have a look at the 18 millisecond points. And with the fixed length of sampling, there is a huge performance drop. But with our proposed variable length subsampling method, the performance drop can be highly recovered. The green line is the result using Hilbert codes as our guidance, and the single purple point is the result using the unsupervised ASR boundaries as our guidance. The unsupervised ASR boundaries gives a very good performance and efficiency trade-off. Also, we can see that using the forced alignment boundaries, we can achieve even better performance with a very large frame period of 100 milliseconds. And this gap indicates that there is still room for learning better segmentations for variable band subsampling. And the ASR performance shows a similar trend as phone recognition. We can see that around 80 to 90 milliseconds frame period, the variable band subsampling performs well. Next, please. And here we move on to the utterance level tasks, intent classification, speaker identification, keyword spotting, and emotion recognition. We found that subsampling does not have a great impact on these tasks. However, the variable length subsampling consistently outperformed the fixed length subsampling in intent classification and speaker identification, around 18 milliseconds frame period. And the remaining tasks, keyword spotting and emotion recognition, seem unaffected by the subsampling rate and method. And also using the unsupervised ASR code as guidance achieves better overall performance and efficiency trade-off while having a larger frame period of 90 milliseconds. Next, please. And here we also discuss the runtime efficiency of subsampling. As we can see from this figure, the reduction in max is significant compared to the original distilled Hilbert model. The variable length subsampling has slightly more operations compared to the average pooling one due to the operation of the CF module. But still, there is a significant reduction in max. Next, please. And finally is the conclusion of our work. We find that different task has its preferred frame rate to achieve better performance. And also found that while the fixed length subsampling can perform well with smaller compressed rate, the variable length subsampling works particularly well under low frame rates. And we also demonstrated that the forced alignment boundaries significantly improve the performance of phone recognition and ASR with a very low frame rate. And now I will hand the stage back to Professor Hao for the final remarks. Thank you.
Okay, thanks Yan and Zichen for the great presentation. And so I hope you are convinced now. I more or less, partially answered my own questions at the beginning. That's the landscape of compressing self-supervised speech models. And we know that there exists, various small models that can achieve competitive performance. But then it also poses more questions now. So different techniques have different strengths. Some techniques will compress the model to a really small size, but they're not GPU friendly. Some models, they might reduce a huge amount of parameters, and that does not affect the overall performance, and so on and so forth. And so how do we actually put them together and compare them fairly? So there are several factors. For example, memory usage, runtime, GPU friendliness, and so on. But for now, I think it's a good time. I'll take this chance to thank the organizers and Hongyi for the great support. And obviously, all credits go to the students and their wonderful work. All right, I'll hand it back to Hongyi.
Okay, so next we will talk about the robustness of self-supervised model. So the members working on this direction, including me and Yu Zhang and Guanbo Huang and Fabian. Okay, so the first question we are going to ask is, are those self-supervised model robust? Okay, so the question is, everyone knows that those self-supervised models are very powerful. But what would happen if in the downstream task, our label data and testing data has mismatch? This is frequently happen. So here, domain mismatch can mean very many different things. But here we consider speech distortion. if the label data is clean and testing data has different distortion, in the downstream task, can we still get good performance by those self-supervised models? The short answer is no. Those self-supervised models are largely influenced by speech distortion in the testing data. Here is some results. So this result is based on Huber. Here we show the performance of Huber on ASR. So here we show the word error rate, so the smaller the better. Here we show the result of clean speech. Of course, it obtained very low word error rate. And we show the result with different types of speech distortion. Here, those different bars represent different types of speech distortion. We do not have to go through the detail here. And it is very clear that with some distortion, the performance of those self-supervised models degrade. And the same observation can be found on keyword spotting, intent classification, and emotion recognition. But before we come to the workshop, we already have some way to deal with this problem. So this is published in our published paper at Librispeech. So what we do is called continual training. So you have a pre-trained model. Usually people train from Librispeech. Then we use some noisy data to continue train the pre-trained model. Then it will become more noise robust. And here is some result. Here is also the result on ASR. Blue bar is the result of original Huber, and orange bar is the result with continual training. And here, QDIS means those distortion has been used during continual training. And so it's not surprised that with this kind of distortion, with continual training, the performance is better. However, we found that continual training is also helpful for unseen distortion, even though some distortion have never seen before during the continual training. Well, the performance of self-supervised models still become better in the downstream task. And the same thing happens on keyword spotting, intent classification, and emotion recognition. So this is something we have done before the workshop, but this is not the whole story. So how have just mentioned network compression. So I do not have to go through the detail again. So here we try knowledge distillation. And as you know, in knowledge distillation, you give your teacher model, your student model, the same signal and want their output to be as close as possible. And we found that after knowledge distillation, the robustness of self-supervised model become worse. So here is some experimental result. Here the horizontal axis means the model size. And Huber is the original Huber, the largest one. And here we use knowledge distillation to compress the Huber to make it smaller. So we have some smaller model in this region. The blue line is the result with clean speech. Of course, knowledge distillation still degrade the performance of a little bit, but not much. However, if our testing data with speech distortion, orange line is the result we obtain. So compare with Huber and knowledge distillation-based Huber, you can find that with knowledge distillation, the model becomes less robustness. So can we do something for those compressed model? Here we have a new way to do knowledge distillation. We call cross-distortion method. We try to do two different setups. In the first setup, we give distorted speech to student and clean speech to the teacher. So teacher take clean speech as input and output clean representation, and student take noisy speech as input, but it has learned to output the clean representation of teacher. So this is setup 1. And in setup 2, we give student and teacher different distortion. So we apply different distortion to speech, to student network and the teacher network. And we still want their output to be as close as possible. And you can imagine that in this way, the student model have to learn to extract domain invariant representation. We also compared our approach with domain adversarial training. So when we train the student model, we can further apply discriminator. So discriminator learn to determine what is the input distortion. We have different types of distortion, and the discriminator have to classify what types of distortion is the input of the student based on student's representation. Then, just as the typical domain adversarial training, students have to learn to fool the discriminator. So this is one approach we try. And now I'm going to hand over to Guanbo to talk about the experimental result. Now, Guanbo, the stage is yours.
Hi, my name is Guanbo Huang, and I'm currently a PhD student at National Taiwan University, and I'll be talking about the experimental results for our work. Next page. And from the results, we will try to answer these three questions. The first question is whether applying cross-distortion mapping during knowledge distillation enhances robustness of supervised learning models, and whether the results are consistent with models of different sizes. And finally, we will also talk about whether domain adversarial training further improves the performance of downstream tasks or not. Next page. And these are the results for cross-distortion mapping under step 1 of ASR. For step 1, the student with distorted inputs learns the teacher's clean representations by observing red bars mostly lower than the blue ones. And by this result, we found out that this method enhances robustness by comparing to original distilled Hubert. And the results are similar for other speech tasks such as keyword spotting, identification, and emotion recognition. Next page. And these are the results for cross-distortion mapping under step 2 for identification and emotion recognition. For the second step, both the teacher model and student model take distorted speech as input. And we observed that for speech tasks such as identification and emotion recognition, this setup yields better performance than the previous setup 1. And this indicates that learning representations of the same speech utterance, but with different distortions, improves the generalizability of the student models even more. And we also find similar results for keyword spotting. Next page. And to ensure that model robustness can't be done just by adding distortions to downstream data during the fine-tuning phase, we also train downstream models with distorted speech data. And the results show that our proposed cross-distortion mapping method still yields better performance under this setting. So for identification and emotion recognition, we can see that applying the cross-distortion mapping of setup 2 improves the accuracy for each testing set. Next page. And we also examine the relation between model size and performance by alternating the number of transformer encoded layers of the student model. The blue, red, and yellow bars represent student models with 1, 2, or 3 transformer encoder layers. By comparing the performance between clean testing sets and distorted testing sets, we found out that the smaller models are less robust to distortions by observing that the blue bar and the red bar have a higher word error rate than the yellow one. Next page. And to ensure general usage of our proposed methods, we trained a smart student model and a larger student model under the second setup, which yield the best performance. And we show the results for the smaller student model that only has 1 transformer layer. And we see that applying cross-distortion mapping reduces the word error rate of ASR. And the results are also similar for larger models. Next page. And we also apply domain adversarial training along with cross-distortion mapping. And for ASR, domain adversarial training further improves the performance a bit. And similar results are also found for tasks such as KS, IC, and ER. Next page. And domain adversarial training also improves under the second setup of cross-distortion mapping for emotion recognition and ASR. Next page. And however, there are also cases where the adversarial training does not improve performance. For example, in classification, the accuracy drops a little bit under the second setup after applying domain adversarial training. Next page. And we'll now answer the 3 questions mentioned in the beginning. So cross-distortion mapping improves robustness of speech self-supervised learning models, and the results are consistent with models of different size. And however, domain observed training sometimes improves robustness when applied along with cross-disciplinary mapping, but sometimes does not.
We head over to Fabian.
Stage to Fabian for the visualization results.
Hello, everyone. So to further understand how these models are robust between different noise distortion, we did some visualization experiments. So next page, please. Just next slide. Okay. So basically what we did was to take the test clean portion of Librispeech dataset, and we randomly shuffled the dataset, and we took 100 points for each of the cases for clean speech and also for the cases with all of the other distortions. And we plot a TSNE representation of the final layer of the pre-trained model for each of these cases. Next slide. Okay, so here we can see the visualization for Hubert model with the original Hubert model. And we can see that, for example, there is clear cluster assignments for Hubert, and similarly for distal Hubert. As we can see in the figure, there is a cluster assignment for Gaussian noise, deep noise suppressed challenge noise, and also reverberation. So this figure is telling us that these models are indeed not robust because are assigning cluster for each of the distortions. Next slide. So yes, as I said, because there is a cluster assignment between each of the noise conditions, we can conclude that Hubert and distal Hubert are not noise invariant. Next. Similarly, we do the same visualizations for the distal Hubert with cross-domain mapping for the second setup when they receive different distortion between the teacher and the student. And we can see that in the left figure, if the teacher model is not continually trained, there is still some cluster assignment for the DNS noise. So the model looks more robust, but there is still some issues there. Nonetheless, we can see that it's very important to have a continually trained teacher, because in the figure on the right, we can see that all the embeddings for the clean and all the distortions lies on the same space. Oh, next slide. So in these cases, we can see that these are a proposal that we have done. It doesn't have cluster assignment for each of the noise conditions, so we can conclude that this method is noise invariant, and also we can say that having a continually trained teacher is important. Next. Okay, so as a takeaway message, we started this workshop with a big gap between performance for distinct models when they are subdued to different distortions. Next one. And we have happily finished this workshop with reduce the gap between these models thanks to using cross-domain mapping and domain adversarial training for protein. Next. As a future work, so we showed at the beginning that there is different ways to do domain mismatch. So we have already done preliminary results, and we have seen that when we do ASR for the Sartre speech, self-supervised models have indeed a huge performance degradation. So we will aim to work on the Sartre speech and children's speech in the future, and hopefully avoiding catastrophic forgetting. So this will be all.
Okay, so I can answer the question if you open the Q&A.
I can read it to you. So Ginny was saying robustness is a challenge to standard ASR techniques. Is it more severe for SSL models?
This is a good question, but unfortunately, it's very hard to answer this question, because if you compare the self-supervised model and the original model without self-supervision, they are originally not in the same level. So if we add noise, we found both models decrease their performance because they have very large difference. So it's hard to tell which one is more robust. So it's difficult to answer this question. However, one answer I could provide is, we know that if we already pre-trained the pre-trained model with continual training, it is apparently that those self-supervised models are more robust. So this probably provide one way for more robust ASR. I mean, if your self-supervised model is continual trained or pre-trained with more diverse noise, this is probably one way to make your ASR system more robust. And for typical ASR model without pre-training, you cannot apply this technology. So I think probably self-supervised model can be more robust because you can pre-train the model with diverse data. And for typical ASR, you cannot do that. So I hope this answers your question a little bit. Sorry, I do not have a good answer. Okay, so now let's move to visual enhanced model.
Okay, thank you very much, Hung-Yi, for the introduction. And also, I just want to say thank you very much for leading the team and doing a really amazing job, and also to the workshop organizers for putting this on. So I'm going to be talking about the work, really half the work that our sub team did. You'll hear about the other half that we did in the second half of the presentation today. But we're looking at what we can do by actually adding multimodal information to these kind of self-supervised speech models. So this team was led by myself and Hung-Yi, and then we had 4 students working on it, Lane from UT, and then Harry, Ian, and Jeff, all from NTU. So I first want to kind of get us all on the same page by explaining what do we even mean by visually grounded speech or multimodal training for these kinds of models. The kind of speech data that we're all used to training on, for decades in supervised training, or nowadays, during the fine-tuning stage of self-supervised followed by supervised fine-tuning is on the left here. So we basically have a speech waveform. Maybe this is somebody saying 2 lambs standing in the grass, and then our annotation comes in the form of some kind of text transcription, or maybe it's, a phoneme transcription, and maybe you have time alignments, maybe you don't, et cetera, but something along these lines. And the kind of data that we're looking at instead is, if you imagine you just kind of got rid of that text, and instead you've just got a photograph of some, 2 lambs standing in the grass. This is the kind of data that we're looking at. But we are kind of thinking about just generalizing this idea to like, well, what if you had speech plus some kind of contextually informative information that wasn't text? So why would we want to train models with this kind of data? Well, one thing that we found is it's actually pretty easy and cheap to collect this kind of data. During my PhD, I was able to collect, basically by myself, 1 million utterances of visually grounded speech, just Mechanical Turk, by putting images up there and having people just freeform describe what they're talking about. We found it was a lot easier, cheaper, and faster to collect that kind of data than it was to put speech data up and have people actually transcribe it, because it's a much more tedious task to do the transcription. But there's, I think, a lot of really compelling reasons why we'd want to look at this kind of data. So I think about 40% of the world's 7,000 languages actually don't even have a consistently used writing system. So if you want to build speech technology for these kinds of languages, you actually need to turn towards, some other kind of learning paradigm. And then the other question is, well, can we also sort of augment the models that we have for, our high resource languages or even our low resource languages where we do have some text annotations by considering multimodal training. And we know that in principle, it should be possible to do this because each and every one of us learns language and acquired language actually without knowing anything about text at all. So we know that this is, this is something that we should be able to do. So the data sets that we looked at, actually, we have many more than this, but we kind of primarily looked at 2. We have like a small developmental one, Flickr 8K. It's about 8,000 images with 40,000 descriptions spoken. We also have text transcriptions for sort of analysis and development purposes of the speech. Then we have a larger one, which is Spoken Cocoa, which is based on the MS Cocoa data set. So we have about 600,000 captions, 120,000 images there. And just to give you an idea of what they look like, here's one of the sampled images from Cocoa, and then just a whole bunch of the text transcriptions for the descriptions that we have for it. But in reality, all our models are going to be training with the spoken version of these. Well, I'll show you how we're going to actually kind of merge and combine speech and text. But before we do that, I just want to give a little bit of background about what's possible to do with these models, and then show you how we're actually bringing these models into the realm of self-supervised learning. So a few years back, we started looking at this problem and developed some of these models, which could basically take in an image without any labels or annotations or anything like that, segmentations, along with a speech waveform that describes the content of the image. And you can basically build some kind of dual encoder network architecture with some kind of like temporal spatial attention, where hopefully if the model kind of figures out the correspondences, it's able to identify like what objects are being described and talked about like at what time in the speech. And of course we don't actually have ground truth alignments that we can use between the modalities to train on. So instead, we have to kind of come up with some self-supervised or contrastive learning framework. And the way that we do that is we basically say, okay, let's assume we can derive some kind of similarity or matching score from this attention map. And then that gives us a measure of how well a particular waveform describes a particular image. So then you can just go in your big bag of training examples and you can take some paired examples and say, well, model, assign a high similarity to these examples. And then you can take some mismatched examples by just taking the captions to the images that don't go with the one that you're holding in your hand and saying, okay, model, assign a low similarity score to those. And as you go through this kind of training, what you actually get when the system is all done is something that can actually do this.
This is a photo of a girl standing in front of a lighthouse. The little girl is wearing a blueprint dress. She has blonde hair and blue eyes. The lighthouse in the background is white with a red roof.
So basically, the model has some emergent ability to recognize words as well as objects and the linkage between them, despite the fact that we didn't train this at all with any kind of text transcriptions, alignments, any supervision in either modality whatsoever, other than just knowing when somebody looked at this image, this is what they spoke. So the question then is, okay, how can we bring this kind of technology and these insights into the realm of self-supervised learning and hopefully reap some of the, the benefits that they bring? So what we did in this workshop, we really asked 3 questions. So number 1 is, well, if we've got these models that can relate speech and text together, speech and images together, but we also know that there's these big pre-trained models like Clip out there, which have text and images that they've learned to relate. Can we somehow leverage these 2 together and think about this as maybe like a problem setting where we have non-parallel speech and text data, but they're both grounded with some kind of visual information. So can we basically marry these models together? And the 2 ways that we looked at doing that are looking if we could basically improve the performance of self-supervised speech models on things like the Shor benchmark or image retrieval from spoken input. That's what Ian's going to talk about in just a moment. And then later today, you're going to hear from Lane, who's going to tell you about how we can actually use these models to improve unsupervised ASR, like wave-to-vec-U style models. So at this point, I'm going to hand it off to Ian. Ian, are you in the Zoom and ready to go?
Hi. Yeah.
Okay.
Okay. Thanks, David. Hello, everyone. I'm Ian Xu, and currently an undergraduate student from Professor Hongyi Li's lab. And before I'm going to talk about our project, I will first introduce the CLIP model from OpenAI. CLIP is a large-scale language image pre-training model. It is trained on 400 million image text pair dataset. The objective is to use contrastive loss to align image and captions to the same embedding space. The total training process cost 12 days on 256 GPUs. So in our project, we utilize the pre-trained CLIP model from OpenAI. Okay, next page.
Oh, sorry.
Okay. To integrate CLIP model into our self-supervised model, we come up with 2 settings, parallel and cascaded. Notice that in both of the settings, we keep the CLIP model frozen during our training process. For the parallel version on the left, we apply an extra transformer encoder layer on top of the Hubert model. And before the transformer encoder layer, we prepend a CLS learnable vector in the front to summarize the audio content. Then we use the same loss as in CLIP to minimize the contrastive loss. For a cascaded version on the right, overall, we use the same way to minimize our loss, but instead of directly summarizing all the audio features from the Hubert, we design multiple CLS vectors. These vectors are used to select some related subwords from the speech utterance. We call the selected subwords as keywords, and then the keywords are passed into the CLIP text encoder to get a final representation. So in cascaded version, our model has to predict the appropriate keywords from the speech utterance to minimize the contrastive loss. I will then explain the details of subword selection in the next slide. Okay, next page. For subword selection, we calculate the cosine similarity between each CLS vectors and the entire CLIP text encoder subword embeddings. And we serve the cosine similarity scores as logics for subword selection. We use the straight-through softmax technique to forward one hot subword embedding and make it differentiable on the backward path. Also, before calculating cosine similarity, we use a Bayesian layer for shifting the output distribution of CLS vectors to enhance the training performance. Next page. Now let's talk about the evaluation we run on this project. First of all, we run the super benchmark, and we only choose keyword spotting and phone recognition in this project because of computation and time limits. Also, for retrieval tasks, we calculate the recall rate for evaluation. We report R at 1, 5, and 10. It means that for n images and a given spoken caption, we see if we can retrieve the golden answer in the first 1, 5, or 10 results. Next page. Now here are the results of the image speech retrieval. On the left, we show our parameter counts of our model. Even though our model are very large, but most of the proportion is frozen during our training process. On the right is our image speech retrieval result. We can see that our model outperforms SOTA models even trained on a small data set like Victor 8K. Notice that we only have about 10 million parameters required for training, so we can train on a large batch size with only little GPU resources. Overall, these results shows the benefit of leveraging CLIP in the VGS model. Next page. Okay, for our parallel version, we also conduct the zero-shot speech text retrieval. The retrieval is done by using the representation from parallel CLIP and calculate the cosine similarity with the output of pre-trained CLIP text encoder. From the results, we see that we are way better than random and also very close to supervised method on large data set like spoken COCO. From this experiment, we think that this could be applied to retrieve semantically related pairs transcription of different languages. Next page. We also conduct keyword discovery experiments on cascaded speech clip. The attention map shows the attention weights for each keyword when predicting the subwords. In our transformer encoder layers, each CLS vector serves as a query. Each CLS vector will attend the entire speech utterance with different weights at different positions, which we show with different colors in the figure. In our experiments, we have 8 CLS vectors in our model, so we have 8 keywords. Large attention weights indicates that our model puts more emphasis on the part of the speech to select the subwords. The words listed on the right are the subwords sorted in decreasing cosine similarity calculated with the selected keyword embedding. So for example, let's look at keyword 4, the red one on the attention map. The color on spoken word sign has the largest weight. As a result, our model predicts the subword sign in the first place. From this result, we show that sometimes our model can retrieve actual hit on keyword discovery. Next page. We also list the top 10 successfully retrieved subword from spoken COCO. From the table, we see that all the entries fall mainly in 2 categories. Either they are high frequent words like articles and preposition, of, in, or they are concrete objects in image like skateboard and street. In addition to qualitative analysis, we also calculate the hit rate for each keyword. The result shows that a larger model has a better hit rate on average. Next page. As for superb results, we see that we have a performance improvement on keyword spotting compared to Hilbert base, but similar performance on phony recognition. This indicates that the VGS model has enhanced self-supervised model on keyword spotting tasks on superb. Next page.
Uh-oh.
So then
This screen went out. What's that? Oh, there we go.
Okay. Okay, let's talk about the conclusion. So we have done several things during the JSON workshop. First of all, we retrieved SOTA on speech image retrieval, and we have conducted keyword discovery on speech utterance without parallel speech text data needed. And also we have done zero-shot speech text retrieval. and we have submitted our recent results to the SLT during the workshop. For some takeaways, in this project, we find that with the help of large-scale pre-trained visual language models, we can utilize speech-text data with only little amount of training. Also, by integrating VGS model, we can give self-supervised model the ability to extract speech content. And for our future work, we might try to combine the parallel and cascaded objective into a single hybrid model to see if we can do better. And also, unsupervised ASR and speech translation is also a promising way for our future work. Okay, that's the end of the presentation.
Well, thank you very much, Ian. And I'm going to hand the presentation back to Hong-Yi.
So I'm going to talk about the integration of different technology. So in the last 2 weeks of the workshop, we decided to put all the effort together to see what we can get. And this part, I have to thank Kai Wei to lead the effort to integrate the models. So you have seen several techniques developed by this team. So I want to know what will happen if we integrate everything and submit to the Superb Challenge. So this is the leaderboard of the Superb Challenge. Here I show the leaderboard of the hidden data set. You can find that it's a 2D leaderboard. So the vertical axis is super score. Super score is the average over 10 different speech processing tests. I'm not going to go through the detail how to integrate the result of 10 different speech processing tests. Anyway, the better, the larger the super score means the better the self-supervised model. And the vertical axis is computational cost. I show max here, and this in this leaderboard, the score is shown in the log scale. And you can find that there are some very large models. There are Huber large, Web2Vector large, WebLN large, and there are some base model. Actually, they seem to be very large on this leaderboard. If you want to know in these two regions which model performs the best, you can find that WebLN large, WebLN base, they are actually the best model in the large model region. But here we are interested in a smaller model. So let's take a look at the smaller model, the model smaller than those base models. So we also submit some individual technology to this super leaderboard. So number 10 here is the result of Distill-Huber. Distill-Huber only have convolutional layer and 2 layer of transformer. So this is the result of Distill-Huber. It's much smaller than the base model, and its performance a little bit worse, but you can say still comparable to the base model. And with cross distortion mapping, so I just introduced this technology. With cross distortion mapping, we can get slightly better performance on the super leaderboard. The model have the same architecture, so same max, but the performance of number 15 with cross distortion mapping can achieve a little bit better performance. So if you are looking for a model even smaller than the base model, probably you can choose Distill-Huber plus cross distortion mapping from this team. And we are also consider, let's integrate Distill-Huber with Mills-Huber. The idea is very simple. In this teacher-student framework, let's remove convolutional layer and replace convolutional layer with log spectrogram. Let's see what will happen. The model is very, very small. The model only has 2-layer transformer, only 2-layer transformer, nothing else. And the model is number 24. It do not really achieve good performance, probably because it's truly too small. So we try a little bit larger model. We try 3-layer transformer, no convolution, take spectrogram as input and have 3-layer transformer. And we get number 29. You can find that this model, although it's not comparable with those large model, but its performance is comparable with the model, which is probably twice number of parameters of the Distill-Huber plus Mills-Huber. And we also try to plus sequence reduction. So insert sequence reduction layer into the model. And we found that sequence reduction, crash speech enhancement, and source separation. So it looks like if you downsample the representation, then the performance degrade a lot on those generation tasks. on super leaderboard, if you cannot achieve good performance on all the tests, then your super score will be very bad. So we do not show the result of sequence reduction here. Then we can apply visual enhanced model. We can add speech clip on top of the model with noise cancellation and male spectrogram as input. So originally in Davis' experiment, they used Hubert. So now we replace Hubert with our model. And this is the result. We get model number 31. So 31 is number 29 plus visual enhanced. Then we get 31. So compare 29 and 31, we get a little bit improvement. And if you compare this model with all the other model with the same computational cost, it is also slightly better than other model. So this is the result of integration. So due to time limitation, we haven't get super good result, but hopefully in the following few months, the team can still continue working on this direction, and let's put some point at this region. So this is my dream. Okay, so this is about integration. Before we move to the Q&A, there's something very important I want to share with you. Probably not all of you noticed that today is Chinese Valentine's Day. So I want to thank for the spouse of all the members. So thank you for let your husband, wife, boyfriend, girlfriend to join the workshop, to hanging out with us. So thank you very much and happy Chinese Valentine's Day. Okay, so now we move to the QA session. Okay. Okay, so.
Thank you.
Yeah, thank you. Yeah, we can about 10 minutes
So,
QA.
guys, time for questions, both for local audience here and online. Online people, please raise your hand so that we can unmute you and you can ask your question.
Yes.
Thank you for this presentation. So I have a couple of questions. One is about the data that you use to do the distillation or compression of the models. How important is to use the same data that was used to produce that model?
Okay.
Some data is data specialized to use smaller data or some data.
Okay. Let me answer this question first. So I think we use the same data, but let Hao answer this question.
Yeah, we use the same data.
Okay, we use the same data.
Do you have you ever tried to use different data? Do you have an idea on how that would impact?
Because we want to control.
Yeah, I think you have to come.
Online audience. Sure.
Right, so let me repeat the question again. So the question is, have we tried using different data for knowledge distillation? And the answer is no, because we want to control confounding factors and want to make sure that we can actually learn a smaller model with the same amount of data and with the same type of data. But I think that's a good idea.
But I think we have tried use different data set, right? Or I think,
not in my
least,
experience.
Okay, at least in the paper of Distill Hubert, we try use different data set. So for example, instead of use the whole Librispeech, we can use only 100 hour. We also try to use, for example, Chinese speech to learn the Distill model. The performance degrade a little bit, but not much. So you can check the paper for more details. This is the first question. How about what's the second one?
So the second question about the cross distortion mapping. So you are a different distortion for teacher and student. Is that better than just using the clean version of the signal for the teacher? I would think that it would be better just to map the distortion version of the student to the clean version of the teacher. By using distortion also the teacher has.
So you mean what? So if you compare the result, you can find that if we give teacher and student both distortion speech, then we get the best performance. So in our paper, in our experiment, we have three setups. One is both student and teacher have the distortion, but different distortion. Another is student and teacher have the same distortion. And the third one is we give teacher the clean speech and student the distorted speech. So the student will learn how to generate clean representation. But based on experiment, the setup with different distortion to both teacher and student give us the best result. But you mean why, right? I think probably because with this approach, then the student have to learn a speech, domain invariant representation. So as we show in our visualization, with this kind of setup with cross-domain mapping, we can map the representation solved by different noise together. So we found that we learn a domain invariant representation in this way. And if you only apply clean data to teacher, noisy data to student, it's not easy to learn this kind of representation. So I do not really have a very good answer to your question, but based on experiment, give different distortion, give you the optimal performance. Please.
Yes, in the compression experiments, basically in many cases adapted supervised methods to the self-supervised case. Anything qualitative in the sense that in the supervised case, method A works better than method B, but in the self-supervised case, it works differently, or was it sort of things kind of similar that it didn't really change the game?
Okay, I think.
Yeah. So the question is, do we learn anything different from when compressing self-supervised model? Do we learn anything different comparing the supervised case and the self-supervised case? The answer is probably not, I would say, in the sense that, for example, weight pruning is not very GPU friendly, but you can compress the most. And then the other ones like low rank and head pruning, they are GPU friendly, but then you can only prune so much. And heads, as we showed in the experiments, are very important. Yeah, and for knowledge distillation, I think this is the one that differs from the supervised case. Knowledge distillation is actually very hard to make it work in self-supervised case. So somehow we only have one positive experiment so far, yeah.
Thank you.
Yes, yes. I have two questions. One is regarding to compression. So I saw you show the result of a sequence compression that reduced into the performance degradation. I was wondering, when you do the downsampling, have you actually tried, instead of through half the data, have you tried to concatenate the embeddings? So in that way, you still reduce the length of your sequence, so you can, because you use the attention, so your computing capacity is quadratic to the length of sequence. But if you do the sequence downsampling, and meanwhile, if you concatenate the embedding, so although you enlarge the matrix, but actually you can do that in parallel when you lift it forward, right? And meanwhile, you still reduce the quadratic attention part. Have you done that about that?
Yeah, so okay, so let me repeat the question. So the question is, have we tried, when we do downsampling, have we tried concatenating contiguous frames instead of throwing away, even frames or odd frames? And the answer is yes. But then, so there are two settings. One is if we actually train the self-supervised models with that particular subsampling technique. And then there's also another one where we actually train the self-supervised model with the subsampling technique. So we actually found out that, first of all, downstream tasks, they all have their own preferred frame rate in some sense. So phone recognition, for example, you can't do aggressive downsampling because phone units are that big. And it's coming at a certain rate. So you can't do aggressive downsampling. Compared to ASR, if you allow larger word pieces, then you can probably do more aggressive downsampling. So that's one thing. And then we also found that you don't actually need to train downsampling with the, you don't actually need to train the self-supervised model with downsampling. You can just take whatever you have, downsample, send it to the downstream, and it will also work well. And I think to answer your question, so whether averaging and concatenation make a difference, because concatenation might maintain more information than averaging, the answer is no. There is really not much difference, I would say. Yeah. I hope that more or less answers your questions. It's a complicated setting, I would say. Yeah.
Thank you. The other question is regarding to the visual enhancement. So I saw you show a diagram. So my understanding is the motivation doing the visual ground speech is that your visual part of the encoder can more robust the noise. But if that is your motivation, have you thought of combining the robust that the cross-domain training approach, apply that to the visual grounding training? For example, when you train the Hoover encoder part, you inject the noise in your audio speech and see that to post the robustness of the model.
Yeah, probably this question is more for me.
Yeah.
Yeah, because we have tried to integrate different. Okay, yeah. So the question is, we have visual enhanced model to make the model more robust. We have other approach, cross-domain mapping, to make the model more robust. Can we blend together to even achieve better performance? Here we have some integration result, but however, I have to emphasize that this result is a little bit different from what you imagine. There is some detail I do not talk about. So the case is like this. So here for 31, it is based on this model further enhanced with visual enhanced model. However, in this experiment, we do not put cross-domain training. Why? The short answer is we haven't had the time to do that. So it is still running. So it's still in the pipeline. So this result is noise cancellation without cross-domain mapping, but with visual enhanced model. If the presentation is tomorrow, probably you will see the result, know that whether integrate them together will be helpful or not. Yes. So yes. Okay, I hope this answers your question. Okay, here.
Yeah, actually, I also want to ask about visual enhancement. It seems to me that it's like you pair image and text bar. But I would say image has more information than text bar. But when you pair and train them and you cluster them, if that causes any issue at all. Also, the example like two labs on the two lab information may be like the color of the lab, or whether it's a sunny day or even like blue sky on the like background. Yeah. So those like reflect your tracing and the cluster.
So I'm sorry, I'm not sure that I understood exactly which what question you're asking.
Yeah, just like the image have more information than text. If that cause any issue, like when you pair them and train them, because you train that they will, because those heavy information that will cause you false function will not add.
So you're wondering if, because there's so many more bits of information in an image compared to a text string, whether there's any issue there.
Yeah.
So we're not training text to image models. Instead, we're training speech to image models, and then also we're training speech models that can basically index into the embedding table of a text-based model and kind of learn to predict like text words based upon that. But I would say that, I mean, yes, it's true. There are more bits of information in a big image than in a text string. But I think the kinds of contrastive learning objectives that we're using to do the multimodal learning, they learn to discard a lot of it, and they kind of just preserve the kinds of patterns that are necessary in order to make the linkage. So basically they extract the representations from the image that are predictive of the text or the speech features. And if something isn't going to be predictive of text or the speech, they, I think that they tend to ignore it more.
So, okay. Lucas?
I have two quick questions. The first one, I was wondering, with an older experiment, you have observed a relation between compression and robustness. I would expect, like, if you have fewer parameters, you tend to generalize a little bit better.
Yeah, so I know your question. You think if we have less parameter, probably the model should generalize better. But the short answer is this is not what we observed.
And then the second question related to compression of visual enhancement, audio-visual learning. I was wondering whether you could use compression. So right now you're training with both modality at once, right? But you can also say, I was thinking whether you can train an equivalent stream of modality, I mean, speech, video, and so on, and compress all some of that together, and would that be some kind of equivalent way? I mean, would you expect to actually try some kind of like a multimodal system by compression?
I mean, we've talked a bit about some things a little bit, but I guess we didn't really kind of look into this that much. I mean, yeah, some of the things that like we found. So for example, like it's much easier to learn higher level, like longer units when you have a visually grounded model compared to a model that's just doing mass language modeling. So if you only do mass language modeling for your self-supervised learning, you tend to learn a lot of subword, like representations that are very predictive of subword identity. Whereas if you do add the visually grounded training on top of that, you actually learn representations that can predict longer spans of speech. And so if you can link that into, you know, some of like the non-uniform like downsampling for sequence compression, where maybe you can actually start doing like sequence downsampling based upon phone boundaries, and then another level on top of that, word boundaries, you could maybe get very, very large, you know, gains in sequence compression by, you know, just automatically by kind of learning the right way to do it. So I think that there's probably some potential there for cross-pollination, but that's not something that we really had time to look at and develop the models for in the workshop, because I think we need to develop some like fundamentally new algorithms in order to do that.
Okay, Didi?
So I have two questions. The first was in the visual enhancement work. I'm just wondering, so those modalities, right, shows what Sir said, those modalities have a fundamentally different information encapsulation capacities. So I'm just wondering, was there an appellation about if the model is relying, say, more on one of the modalities representations that you're eventually using? Because, and is that also representative of the task that you're using to evaluate? Because in the task that you're using, perhaps it would be better to use more tasks that are more speech representation reliant rather than like image representation reliant, which is what it looks like. So I'm just wondering if something like that, did you do an embedding analysis of some sorts, or maybe more tasks that were more representative of this kind of shift? Because it is possible that the image embedding representation is being relied upon heavily, and the speech representation is just like lossy compression, some additional information coming into the model.
Do you mean in like the downstream tasks like on Superb doing the phone recognition and things like that?
Yes, that and then the additional analyzes the speech embedding representation, but not like take the most lossy compression hit in the eventual representation.
Yeah, so that there's an interesting aspect to that question, because actually all the experiments that we did only used the speech representations. So the images were only used during training as kind of like a supervisory top-down signal. And so, and those models were like the image encoder that the pre-trained one we used from Clip was actually frozen the entire time. So we basically freeze it, use it to extract the target for the self-supervised training for the speech model, but then throw it all away and just use the self-supervised speech model. And what's kind of cool is we never really changed the self-supervised speech model architecture. We're still just using the same like 12 stack transformer model as Hubert. So we were really able to investigate like just surgically like changing the objective function and what effect does that have, keeping the architecture constant. The thing is though, I actually do think that there would be benefit, like you suggest, in actually bringing the multimodal information into some of the downstream tasks. So can you basically add context to doing like low, you know, sort of like low resource ASR with something like the Superb benchmark? I mean, I don't know if all the tasks as they're currently formulated would completely benefit from it, because, you know, like we're doing like decoding on Librispeech instead of like, you know, visually grounded speech data. But if we did develop a task, which maybe we should do, that does have some kind of contextually informed speech, then maybe we could actually use the multimodal input to get better results than we could just with the speech alone. So thank you. That's probably something we should do.
There's an online question.
Yeah, but there's also another question.
Speaker was waiting for some time.
Okay.
Go ahead, Peter.
Okay, thanks. Can you hear me?
Yes. Yes.
Okay, great. So yeah, I was wondering about the results on MetaHubert that you presented in the beginning. If I saw the figure correctly, it looked like there was still quite a gap to the original Hubert, and I would be interested in your take or your explanation why why we observe this gap. So do you think it's because we are not doing waveform modeling and lose some information there, or possibly it's just because of the difference in the model size, or maybe you have some other explanation? I would be interested in that. And maybe as a follow-up question on that, do you think this is specific to Hubert because of the use of MSCCs there or similar, or do you think that would also hold for Wave2Vec 2.0 or other related approaches?
Yeah, okay, so the question is, why is there a gap between male Hubert and the original Hubert? And the modification here, the major modification here is removing the CNNs, and we try to maintain as much as we can the training procedure, but then, it's very hard to actually maintain everything. That there are small differences here and there, and we just don't know whether those small differences will actually contribute to the final performance. So I don't have a clear answer yet, but we're looking into this. And in fact, training these models are slow. So we spend 2 weeks to just have a model to look at. And so I actually don't know. So we try to maintain, to the original pipeline as much as we can, and that's what we get. And we do see that, all of the claims in the paper, for example, doing 2-stage training, using the k-means of the acoustics as targets, all of these are beneficial. So we can confirm that. But then we're just not able to match the original Huberts, yes.
Okay, yeah, thanks for your take on this.
So I have a question along the same lines with Mel Hubert. I mean, you are comparing Mel Hubert with the Mel part, the feature extraction component, a fixed transform versus a data-driven transform, which is CNN, on kind of the same domain data. Have you run any experiments where you compared the two, let's say on telephony data, on totally out of domain data? I would expect that's where you would see the gap close, or even Mel Hubert may even outperform CNN-based Hubert. Do you have any results?
No, unfortunately. But then you should also doubt that, the CNNs are only looking at so few samples in the waveform. So like how much can the model, I mean, yeah, there are 7 layers of CNN, but how much can you extract from that few samples, like a few hundreds of them, really. So that's the motivation of replacing it with log males. But yeah, we don't really know whether that'll make a difference yet. So maybe more analysis are needed, yes.
Yeah, and also.
Oh, sorry, go ahead.
So how much of these results, especially with the noise robustness, do you think will hold the conclusions if you use the model like WaveLM that is trained with data augmentation?
Yes.
Do you think the results will still hold, or conclusions?
Yes, okay. So your question is, we know WaveLM is trained by augmented data. Then what will happen if we test them on the distortion setup, right? So the good news, I know there are lots of Microsoft people online. So the good news is WaveLM is very robust. So if we compare WaveLM with the Hubert, it's more robust than Hubert. We do not put the result here, but it's more robust. However, compared with continuous training Hubert, continuous training is more robust than WaveLM based on our experimental result. But I know your question is, then why don't you do continuous training on WaveLM? The simple question is, we do not do that. we haven't tried it yet. So this is all the result I have.
Short one related to Mel Hubert. I was curious if you had made some analysis, spectral analysis of the convolutional layer of Hubert to see whether they are comparable as a Mel Hubert or extra.
Dave, you want to say your experiments?
Yeah, so this is a side project that I was just doing by myself the last couple of weeks on this, like basically taking the convolutional features, and it can actually do like a frame to frame, 1-to-1 thing, because it's like, okay, 400 samples with a shift to 320, and then basically like building models and seeing like, can we reconstruct log-mel filter bank spectrograms and then like visually see what's missing or what's there. I don't have any like super solid results yet, other than just very anecdotal observations. Very easy to reconstruct formant frequencies, very difficult to reconstruct harmonic structure. Also, if you add a little bit of noise, it's actually, you can kind of guess, like you can add noise to the MEL spectrogram enough to like sort of cover up higher formants. And then when you just take the model that was trained to predict the spectrograms from the convolutional features, that can actually fill in some of those missing formants. Again, this is all like anecdotal, just me looking at spectrograms and not actually, you know, doing any real numerical experiments here. So take it with a half a cup of salt. But yeah, I think it's an interesting thing to look into.
A follow-up question to this Hoover versus male Hoover. So when you compare these two models, what is your kernel size and the strength for the time domain Hoover versus the male Hoover? So when you say male Hoover, you can solve this number of 20 milliseconds or 10 milliseconds. But what is the strength of when you do the time domain Hoover convolution? Did you align them exactly? For example, if you have 160 samples shift in your kernel, so you have the same resolution versus the male Hoover. What is the kernel size?
Are you asking for the spec of the original Hubert? I mean, the original Hubert, they have 7 layers of CNN. I think the effective receptive field is 400 samples, right? With a 320 sample shift. And then, and obviously it's like a 20 millisecond shift. So it's not the usual 10 millisecond shift in log mail features. But for mail Hubert, we just use the default, you know, de facto log mail implementation, like 10 millisecond shift.
Oh, but I think it's the same as the 20 millisecond mail Hubert, right? Because
Yeah. So
if you downsample by a factor of 2,
exactly. So we also have a downsample version of Mel Hubert to match the frame rate.
I see. So when you compare those numbers are aligned in track.
More or less, yes.
So probably we have to end this session here because we're already behind the schedule. Yeah. So originally we planned to start the second part at 11. Are we going to still have a break?
Have a short break.
Okay, so how about we get back at 11:05? Or you want to get back at 11:10?
11:10.
Okay, so we get back at 11:10. Okay.
Thanks, Sanjeev, and thanks, Hongyi. Yeah, I think we will be behind of schedule. So let me just go ahead. So you already have seen like there are lots of great works to do self-supervised learning for speech models. The second part, we are going to talk about like what are the different ways we can better leverage pre-trained or self-supervised learning models to accomplish different kind of tasks. And I will begin with the first part, how to efficiently use self-supervised learning models through adapters and prompting techniques. This work has been done by lots of students like Kai Wei, Ziqing, Alan, Zhiying, Hua, Fabian, Yukai, and Shu. So all the credits go to the students. They have to do all the hard lifting works. But why we want to explore like adapter or prompting? So to give you a little bit like background, like this is how the recent or ways to leverage the self-supervised learning works. Like you pre-train your models with some unlabeled pretext text. After that, you have several downstream tasks like keyword spotting, ASR, different kind of things. And then you fine-tune your models. By fine-tune, I mean that you pretty much use your downstream labels and to use that as like the supervised learning signals. And you might have like different kind of laws and you tune your hyperparameters of the entire networks. But as you can imagine, more and more like a complicated use cases, especially industry, usually there are lots of different type of downstream tasks. If you need to tune your models for different type of downstream tasks, it can be very efficient in terms of computation, in terms of memory or disk usage. So there are like increasing interest in exploring how to efficiently tune your self-supervised learning models. So here, like prompting and adapters are two very promising techniques, has shown a lot of efficacy in NLP areas. The prompting, it's ideas that pretty much add some tunable parameters ahead of your inputs. Like here, we show like before the input of keyword spotting or ASR, we add some like tunable parameters. And another type of works is adapters. You can imagine as a kind of thin layers you add it in between your self-supervised learning models, and you only tune your adapters. I should also mention like here, the color coding is like if it's in like a red or blue are the tunable parameters, and if it's in gray, it's a fixed or false. So as you can see in these ways, you probably can just tune a very small amount of the parameters for different type of downstream models and achieve comparable performance. Through that, we want to achieve a more efficiency. So we want to, of course, comparable or even better performance and saving computational resource, or even achieve better, more robust models through these kind of technologies. So give you a little bit more details. This is adapters. The right-hand side, it's first is a visualization of the transformers, and each color code blocks are different type of adapters people are exploring. Like bit feed or high speed, different kind of things are added in a different architecture, added in different place of transformers to provide these adaptation capabilities. We're not going to too much details, but in the later we're going to show like after our experiment what are our findings. The second type of works prompting is a high level is that on the right hand side you can see like we first pass through audios to some encoders, like you probably hear like a wave to back 2 or Hubert. These are those self-supervised learning models to do the encoding. And after that, we have uni language models. This can be imagined as like GPT-3, but it's trained on like the quantized tokens from Hubert and to generate the quantized tokens. And after that, we can add like several like tunable parameters to the uni language models so that the uni language models can generate labels directly for different type of tasks. Like here, we show like intent classification, and you generate like what's the action, what's the object, and what's the location. You might wonder like why like the uni language, what uni language model is. The short answer is it's also a type of the self-supervised learning models. For now, we are not adding the prompting in the encoder part. The reason just because it's better fits to the uni language model parts and the better fits how it's explored in NLP. But in moving forward, we definitely want to see like whether we can add like prompting to the encoder part. So that will be the difference. To give you a little bit more details how this works. So first, we take ASR as an example, and once we have the audio and we pass through Hubert, these Huberts are fixed and they generate like unit tokens, and you pass through a unit language model. Because we are exploring prompting, so we add like several like tunable tokens here to reconfigure these unit language models, and then you can generate like auto regression ways to get the output. And after that, we are going to need verbalizers to do the mapping from the unit tokens to the characters and to get the final results. Like here is a cat. Here just some like more information about like what is the unit language model. I'm not going to do too much details, but the take-home message is it's a first generative speech language models trained on large corpora about like 6,000 hours Librelite. So that's why it has these capabilities to take units and generate another sequence of units with some like semantics and the different information encoded there. So we take this unit language model as our like first step to explore. So this is basically the high level of the works, how adapters and prompting works. And the next, I'm going to have Alan to talk about how adapters works and what are the experiments we're exploring. Alan, are you online?
Hi, I'm Alan Fu, and thanks Daniel for introducing the methods. For now, I'm going to talk about experiments. And for adapter, we focus on 3 points. The first point is that does adapter methods work on superf? Second, what's the benefit of using adapter methods? Third, is there any specific finding in speech or different from other areas, such as natural language processing? For the first point, we conduct different methods to superf benchmark. As shown in the first column, we compare fine-tuning, baseline, and different adapter methods. The second column represents trainable parameters in the upstream model. From this table, we can find that adapter methods yield comparative performance with few trainable parameters. Next, please. This page, we compare the performance of different adapters. The architecture of adapters is shown in the right part. From the previous result, we find that high-speed adapter performs best, while LoRa adapter performs worst. Moreover, weighted sum is a powerful technique in superf with just tuning 12 parameters in the upstream model. If you are more interested in result, you can refer to page 134. For second point, what's the benefit of using adapter? For the left figure, we conduct experiment on phone recognition with different sets of training data. We can find that adapter method perform better in lower training data. In addition, from the right table, we train different methods on different learning rates, and we find that adapter methods have more tolerance of learning rate compared to fine-tuning. And here is the last point. Is there any specific finding in speech? The first thing is that weighted sum is especially useful in superf benchmark, while in NLP, weighted sum is not a common technique. There's a paper called the What's Analysis of the Self-Supervised Speech Representation Model, and they find that the output representation from each layer contains different speech information. Thus, from this point, weighted sum is able to leverage the information from different layers and receive comparative performance. Another point is about LoRa, which is a powerful adapter method in NLP and is added to the attention module. However, LoRa did not work on superf. Thus, we conclude that adding adapter to the attention module is not effective in superf. A better way is to add adapter behind the feedforward layer, such as high-speed or adapter bias. And this is the end of adapter results, and I will hand the microphone to Hua to talk about prompt.
Thanks, Alan, for introducing the adapter methods. Next, we focus on prompt tuning method for speech processing tasks here, where we aim to investigate 3 questions. Firstly, does a prompt tuning method work? Secondly, is again generalizable? And thirdly, how to make prompt tuning method better for speech processing tasks? Well, to answer the first question, this table compares the results of prompt tuning named PT and fine-tuning named FT methods on keyword spotting and intent classification tasks. We evaluated both Hubert and CPC representations here. From the table, we can see prompt tuning method use less trainable parameters than fine-tuning method, but can outperform it on 3 out of 4 task scenarios. Especially, we can observe on the intent classification task with CPC representations, the prompt tuning method can significantly improve the accuracy than the fine-tuning baseline. Well, besides, we also want to know is again generalizable to other speech classification tasks here. We apply prompt tuning method to another 3 speech classification tasks, including LT, DM, and Arabic speech commands recognition tasks on the Hubert representation. From the table, we can find prompt tuning method can have good performance on different speech classification tasks, which shows its generalizability. And prompt tuning method significantly improves the performance than the fine-tuning baseline on all the 3 low-resource speech command tasks. Well, furthermore, we investigated how to make prompt tuning method better, where we propose a linear verbalizer method here, which uses a neural network to learn a mapping between the pseudo classes of the unit language models with the ground truth data classes. In comparison, the frequency-based verbalizer is a baseline approach, which sorts out the top frequent pseudo classes to directly be the ground truth labels. The results in the table show that linear verbalizer can always improve the accuracy of the prompt tuning method on the 2 speech classification tasks with both Hubert and CPC representations. Well, these contents briefly conclude the experiments of the prompt tuning method. Next, I will give the microphone back to Daniel for our conclusion part.
Yeah, thanks, Ellen and Hua. So to summarize, as you can see, like we have done a very thorough studies over like adapters and prompting in speech supervised learning models. And they demonstrate like it can yield like comparable or even better performance with fewer parameters. Like adapters shows gains over a range of different type of superb tasks, and prompting is mainly improves a lot in classification and sometimes low resource classification tasks. We also discovered some additional benefits like data efficiency or like robust against learning rates. And we also made 2 submissions, one accepted by Interspeech to talk about our works. Regarding the future work, this is definitely very promising directions. We want to continue the exploring like different areas, like more techniques to improve the performance and efficiency, or exploring like more domains or more challenging tasks to see how prompting adapter can move forward. So let's conclude the part, and I'm going to hand the microphone to Sam. And Sam is going to talk about more like prosody related tasks.
Okay, thank you. Okay, yes, so this is 15 minutes on self-supervised learning for prosody. Next slide, please. So we had 2 questions. And at the start of the summer, we did not know the answer to these 2 questions. Nobody knew. First question, are pre-trained models useful for prosody intensive tasks? Right, so as you know, pre-trained models, don't show that yet. As you know, pre-trained models are mostly trained for self-supervised tasks or speaker identification or speech recognition. Prosody intensive tasks, things like determining when to take a turn or detecting sarcasm, those are sort of not in the scope of training of loss functions for most self-supervised systems, and they're not something that have been tested. So existing benchmarks, before we added our new benchmark, never tested anything that really tested the ability of self-supervised learning to capture prosodic information. So are they useful? Do they learn prosodic features and patterns? And the short answer is next. Yes and yes. And this is, the details are in a paper that we've submitted to SLT, but we're just going to give a quick overview of the key methods and the key findings. Next, please. Okay, so on the left, so we did many experiments, but focusing on the 2 left categories, the state of the art in prosody is use handcrafted features, open smile or something similar, where based on decades of experience with what prosody is and how it represents meanings, the features are very cleverly designed, fed into a powerful model like a recursive neural network, and that gives you state-of-art results. So that was our arrival. We tried to do something with a very simple linear layer on the assumption that maybe the pre-trained models have already uncovered everything that's important in prosody, and so a linear layer would suffice. So those are the comparisons. There'll be other results in the slides, but that's the key thing to focus on. Next, please. All right. And now for the details on the experiments and the results, I'll turn it over to Leo.
Okay, hi, I'm Qiren Feng, and I am a master's student in National Taiwan University. So I will introduce about our framework. Previous slides, please. And it is our framework. Our framework is use powering task to measure whether the outputs of SSL model have prosodic information. And the below graph is our pipeline. First, we will have utterance. Then we will pass to the upstream model, which can be for the bank or Hubert. Then we will pass to prosodic related powering task, for example, sentiment analysis. Then we will get a matrix, which can be accuracy to show whether SSL model can achieve good performance on this powering task. And actually, we use 16 upstream models with 5 powering tasks for powering prosodic information. Okay, so then I will talk about our experiment setup in prosodic test and our upstream model. Okay, next. Okay, for our powering test, because we have 5 powering tests, we can split these 5 powering tests to 2 categories. The one is prosodic intensive task, and the other is pseudo task for prosodic. So I will first talk about the prosodic intensive task. Next. We have 3 powering tests in this category. The first is sarcasm detection, which is given an utterance. We want to predict whether it is sarcastic or not. And the dataset we use is the mustard, and it is a binary classification task. The second powering test is sentiment analysis. It is given an utterance. We want to predict the sentiment of it. Because sentiments have multiple sentiments, for example, happy, angry, and so on. So this is a multi-class classification task. The dataset we use is CMU mosaic. And the third powering test is possessiveness prediction, which is given an utterance. We want to predict whether it is possessive or not. The dataset we use is PON, and it is a binary classification test. Next. And the second category, we have 2 powering tasks for this category. The first one is prosodic reconstruction task, which is given an utterance. We want to predict the pitch and energy for each frame. Because we don't have this label, so we have to generate by ourselves, and we use PyYet, which is an open library. The dataset we test is LibrisTTS, and actually it is a regression task. So the overall pipeline will show below. The utterance will pass to the upstream model, then pass to the linear model to get pitch 1 to pitch 5 in each time. Then we will also put the same utterance to the PyYet to get pitch 1 to pitch 5, which is the ground truth label. Then we will compare between the pitch 1 from the upstream model and the pitch 1 from the PyYet to get the log mean square error to show whether the SSL model can reconstruct the pitch or energy information. Okay, next. The second powering test is future value prediction. Actually, it's very similar to the previous test, which the only difference is it is predict the future pitch energy for each frame. So the dataset is same, and it is also regression task. So the utterance will pass to the upstream and pass to a linear model to get pitch A to pitch E. Then we will also have the similar utterance to pass to PyYet to get pitch 1 to pitch 5. Then the goal of pitch A is to predict the future value, which is the pitch 2 as time equal to 2 in the right-hand side. And we will get the log mean square error. Then we will show that whether the upstream model can predict the future pitch or energy. Okay, next. Okay, so for the this is for the powering text setup, and let me introduce about our upstream model, because we select 16 models, which include traditional model, including for the bank, and also including SSL models, for example, Web2Vector 2 or Burst or WebLN. Okay, then that's granting to introduce our main results.
Hello, I'm Guanting Lin from National Taiwan University, and I'm going to share our result on this prosody paper. So next, please. Okay, so we actually found out that self-reliant model performed very well on the prosody intensive test. So from the result of this task, this is a sentiment analysis test, and we first see that the red line is the SOTA performance from previous paper using only audio, and the green dot line is the text baseline, and the blue dot line is the Evain feature baseline. And we can see that all the self-supervised model outperform the baseline FBAM feature. Yeah, and WaveLM and Huber Large even yield performance better than the SOTA and very competitive text-only baseline. And yeah, next please. So, and this is a result for the sarcasm detection downstream text. And we can see that the text-only baseline has a worse performance, which indicate that this downstream text require acoustic information beyond content for the prediction. And although some self-supervised models show an inferior performance to the baseline FBAM feature, other SLS models reach remarkable performance, like Distill Huber, and WaveLM even achieve better performance than the previous SOTA. Next, please. And for the persuasiveness prediction, we observed that all the self-supervised model yield better performance than the FBAM feature and the previous SOTA in a large margin. And also like APC, VQ APC, and VQ Way2Back and Huber obtain better accuracy compared to the text-only baseline. Next, please. And well, the result above suggesting that SSO model might encode useful information for the downstream task. But here we report more direct evidence from the prosody pseudo task. And first, we see the result of prosody reconstruction on pitch. Here, the smaller MSE value means better performance. And here, the SOTA referred to the off-the-shelf pitch extractor named Reaper, and Reaper will provide a reasonable good reconstruction performance as the baseline. And from this result, we can see that several SSO models surpass Reaper and the FBAM feature, but except for the VQ Way2Back and Way2Back. And we can see that the best performing model is the WaveLM and outperform the SOTA in the large margin. And from this result, we can conclude that SSO models store good representation for the prosody information. Next, please. And here is a result that SSO model can predict future prosody. And this task is more challenging than the pitch reconstruction since it requires the model to capture global and local prosody information to predict the future. As a prediction horizon become larger, the text is more challenging. And from the result, you can see that Huber Large gets the best performance across all the prediction horizon and significantly outperform other SSO model and baseline FBAM plus RNN in all four horizons. And although some SSO model pre-trained objective is future generation or discrimination, they obtain inferior performance to like Huber model. Yeah. Next, please. And we are going to share our further analysis on the SSO model for prosody aspect. Next, please. So we do the layer-wise contribution analysis. We want to analyze that what kind of layer is important for the downstream text. So we analyze the contribution or weight by the weightism mechanism. And for each layer, the higher value of the weight or contribution means the layer is more important for downstream task. And we can see that for most self-supervised model, the contribution is aggregated in the first view layer for the pitch reconstruction and the energy reconstruction. This showing that SSO model tend to store prosody information in the front. And for the classification tests like sarcasm detection and persuasiveness prediction in the figure C and D, the distribution of the layer contribution is smooth, suggesting that both prosody information and content information are important for sarcasm detection and persuasiveness prediction. But for the result of sentiment analysis, we can see that very high contribution in the later layer for the Huber model and the WaveLM model, since previous work have already shown that later layer in Huber mostly extract content information. The analysis indicate that SA might only need content information to perform well. Yeah, next, please. And to further verify whether information stored in the first view layer bring benefits for the downstream text, we use a feature integration experiment for the Way2Back and Huber model. And we compare two settings. The setting one is low level enhanced, and the first, which means that we will use the first two layer and the best layer we discover. The best layer means that determined by the contribution analysis, which obtain the largest contribution, marked with the underline. And the setup two is neighbor layer. So we will use the layer, the best layer with its two neighbor layer with the similar information. And for result on the sarcasm detection and persuasiveness prediction, we see that first few layer help self-aware model get better performance, which means that low-level information improves the modeling. However, the integration of low-level information does not improve sentiment analysis performance, which suggesting that the SA may only rely on content rather than just low-level information, and we might develop a new speech sentiment analysis corpus to highlight on prosody or paralinguistic aspect. Yeah, so that's that's all of my result, and Sam, please share other case study or result. Yeah, thank you.
So given all this previous work, if you can see across the entire pipeline, pretty much English is pretty much used across all this entire pipeline. And it really begs the question of how generalizable these results are to a multilingual setting. Cue the recently released Fleur's dataset, which features 2009 NWay parallel sentences from 102 languages across Eurasia and Africa. It's about 1,400 hours of read speech from Wikipedia, and they provide some labels, but no pitch labels, which is the task that I was going for. So this is a data example. These are all parallel sentences. Try to see if you can hear the different relationships that each language has to the prosody. Mandarin and Zulu are both tonal. Yeah, I can try with the mouse. Okay.
The winter can be deceptively chilly. Temperatures rarely go below freezing, but the wind and humidity combine to make it feel colder than what the thermometer says.
Yeah, and then Mandarin.
冬天可能会比看上去更显得冷，温度很少低于0度。但
And then surrounding Kurdish.
پلەیکەرمی زۆر بەدەگمەن بۆ بەستان دادەبەزێت بەڵام باو شێداری یەک دەگرن بۆ ئەوەی هەست.
And Zulu.
Ubusika bungaba nzima kakhulu. Amazinga okushisa angase adlulele ngale kweqhwa, kodwa umoya kanye nomswakamo.
Yeah. And so basically, you can hear that there's some sort of differences, and we want to model this. And so we want to see how well we have this cross-lingual transfer of prosodic information. And so given the pitch reconstruction task, you can see the model from before, and we're basically doing the same thing where we're taking a waveform, we're extracting the pitch info with PyApt, we're also feeding into a pre-trained model, extracting the hidden states, running it through a linear regressor, and seeing what we can reconstruct. And so PyApt is pretty good for this task because it is in some ways claims to be language independent, and it's based off of signal processing, which helps that. So here's a sample result. These are the same 4 audios that we heard. The red is what PyApt extracts from it, and the gray is what I was able to reconstruct from Hubert's hidden states. And it's honestly not too bad. There's a lot of noise, but it isn't completely awful. And so here are some results by language. The red bar is English and the black is the average. Interestingly, English is worse than average, which is a pretty interesting result, indicating that there is some pretty high generalizability here. And then to break it down by layer, I have the same results that they saw earlier, where in the earlier layers, it does seem to do better. There's more pitch information encoded in those first layers. Then I started looking at some trends. So Fleur's provides us with this language group ID. I didn't see, there isn't too much of a variance. It's the Chinese, Japanese, Korean languages seem to have a very high variance within the layers, but overall it's not too large of a difference. I also broke languages down into tonal, non-tonal, and pitch accent languages to see if there was a difference. Interestingly, tonal languages do perform slightly better and pitch accent languages perform slightly worse. We're still not sure exactly why this is, if it's, but is an interesting trend to keep in mind. And so general conclusions are that pre-training a model on one language can be enough to teach a model transferable methods to extract pitch information. At least we've shown this for Hubert, and it indicates that pre-trained models can be highly effective for tasks involving pitch information in a multilingual setting. And I think this could also be very useful for doing these tasks on low resource languages where we don't necessarily have the resources to pre-train massive models on data from them.
So this is just the summary. So really, I guess there should be two first prizes because in many cases, we weren't able to outperform the state of the art, but in many cases we were. So understanding which tasks and which models are suitable, that's the question for future research. But the bottom line is pre-trained models are really competitive if you're interested in getting performance in prosody intensive tasks. That's it, thanks.
Okay, thanks the speaker again. Let's move to
Okay, so for my part, I will talk about using the pre-trained model on code switching ASR. And so this work was actually done with the pre-trained team and the multilingual team. So when we talk about code switching in speech, it's actually using 2 or more languages in the speech. So you can just switch a word in a sentence and use another language instead of using your native language, for example. And so I think that most of us or all of us can use and will use code switching in everyday life. But then depending on the person, it might take some different forms. So for example, I could use some English words every 100 of words, but some other people would use English every 4 words. And so because of that, it's really difficult to find some good examples of code switching speech because you don't know when code switching occurs. And so for the workshop, we wanted to address one particular question, which was if you see code switching speech as some kind of low resource language, so can you apply some typical ASR approaches to the code switching data? And also we wanted to try to use the pre-trained models on the code switching speech. So for the experiments, I will always use this data, which is from soap operas. It's from 4 different South African languages. So each time you have one South African language, and then you also have English. And so in total, for the 4 pairs of languages, there is 15 hours of labeled data. Moreover, we also have 200 of unlabeled data. So this time it's also soap operas data. The thing is that this time all languages are mixed together. So you don't know when you have one Sesotho, etc. And then we also have some monolingual text. So here I will just show you briefly what the code switching in so these soap operas are. It's unlabeled data, so I won't be able to say what exactly the language is. So I just show you.
Huh? Yazi sine special nje sama spicy hot. Samba ne papa na chakalaka. Ufuna hot, ufuna extra hot nje. Choose masketela. Ngiyabonga.
So I think that you recognize the English words. So that's an example. And then for the label data, so here you have the 4 languages, or the 4 pairs of languages, and each time you have at least 1 English word, but sometimes it's only, well, just family, so 1 word, and sometimes it's really an expression. So the main objective of the workshop for me was to try using the pre-trained models to do some ASR on code switching data. And the first thing was trying to compare MFCC features with the features extracted from some self-supervised models. And then we use as baseline an hybrid model. So the acoustic model is a TDNN, and then we tried using the MFCC features to train these TDNN layers, or we used the features extracting from the XLSR model or the Hubert model. So briefly, the XLSR model is an SSL model, but it's trained on multilingual data. And for the UBERT, it's only trained on English unlabeled data. And then I think I only mentioned it before, but then when I extract features, I freeze the weights. So here are the first results. So in blue, you have the baseline. So I use MFS features to train the TDNN acoustic model. And then I also have the UBERT model used to extract features. So this time I did 2 experiments. One is using the last layer of the UBERT and to extract features, and the other one is using the 6th layer of UBERT to extract the features. And then I also added these 2 green experiments. So instead of using UBERT, I used the XLSR model, and again, it's with the last layer or with the 6th layer to extract features. And so it turns out that in any case, using the SSL features is always better than using the MFS features for my particular experiments. And then for UBERT, it's sadly better to use the last layer. And for the XLSR, it's quite difficult to say which layer is better, but in any case, XLSR is better than UBERT features, which is better than MFCC features. The second thing that we tried was to study a bit more the pre-trained model. So this time I will introduce what we call the MMCC-MGB model, which is just a model trained on only supervised data. It's trained on MFCC features. The architecture is this time a CNN CDNN, and then the supervised data which was used is the MGB dataset. So it's British English and BBC. So you have some, it's kind of in domain compared to our South African data. So it's always labeled. So this is the first pre-trained models with supervised training. And then we use it to continue training on the labeled data from the soap operas, so the South African data. And then you also have the XLSR model from before. And this time it's pre-trained with only waveforms and unlabeled data. And you have the multilingual setup. So again, you have the baseline in blue. So it's using the MFCC features. The acoustic model is trained from scratch. So I also have all of the language on each one. And then in red and orange, you have the pre-trained model. So on one hand, it's the pre-trained model with supervised pre-training. So the MFCC MGB, the white one, and the other one is the XLSR, so unsupervised pre-training. And surprisingly or not, if we use the documentation, so it means just speeding up the audio or just slowing the audio, it turns out that XLSR features or using the XLSR to extract features is better than using the pre-trained model on English data, on labeled English data. So overall, we have 2 takeaways. The first one is that the features with the SSL models are better than the MFCC features in the code switching data. And then if you try to compare the 2 different types of pre-training, so the supervised pre-training and the unsupervised pre-training, turns out that the unsupervised pre-training with the XLSR gives a better result than using a supervised pre-trained model. And so remember that I said that we have the labeled data and the unlabeled data. So we still have the 200 of unlabeled data that I didn't use for the workshop. And so for the following few weeks, I will use this 200 of unlabeled data to adapt the SSL model, and then run again the pipeline. That is to say, just extract features with this adapted SSL model, and then train the TDN layers on the supervised data. And ideally, if we have the time, we also want to use some semi-supervised learning still with this 200 unlabeled data. That's it for the ASR and code switching and pre-trained models. Thank you.
Cool.
Thank you very much. And so we are coming to the next section, which is the self-supervised learning with unsupervised ASR. And this is we are having a very large team. And in terms of that, we'll be handing the mic to Dongji first and to get into the overview of our section.
Yeah, so hi, I'm Dongji. I'm a PhD student at Johns Hopkins University. And this is our sub-team. And we have Lane, who works on unsupervised ASR training using the visual information. And we have Jatong here, who works on applying the supervised ASR model on the other downstream tasks. And I'm going to introduce our implementation of the unsupervised ASR. Next, please. So previously, to train the state-of-art ASR model, we need a large amount of paired speech and text data. And this can be hardly applied to low-resource languages or dialects because of the limitation of such data. But the development of the unsupervised learning makes it possible, since we can first pre-train our model on a large scale of speech only, and then fine-tune it on the limited paired data we have. Now it goes one step further to the unsupervised ASR training, where we can directly train our model using the speech and text data at the unpaired data. Next, please. And recently, Meta published a paper in which they proposed their state-of-art unsupervised ASR model called Wave2Vec-U2 using the adversarial training. And this figure is the architecture of the model. It used the Wave2Vec 2.0 as the feature extractor to extract feature from raw wave file, and then it passes it to the generator to generate phoneme sequences. And the discriminator will try to distinguish between a generated phoneme sequence and the real phonemized unpaired text. So the main idea of the serial learning is to force the generator to generate phoneme sequence that can match the distribution of the phoneme language model from the real text. And there, if we take a closer look at the generator, the structure is quite simple. It just has a batch norm layer followed by a linear layer and a convolutional layer with strat 3. It downsamples the acoustic representations to match the phoneme frequencies. And the Meta also published the code, and it was implemented in FairSync. So during the workshop, we re-implemented and supervised ASR model using ESGNet for a couple of reasons. The first one is about the flexible front end. So in the FairSync implementation, they used the Wave2Vec 2.0 as the feature extractor, and it is fixed in their script. But it is also worth to try different self-supervised models like Qbert or WebLM. But we don't want to spend extra time to prepare our script for each of these models. Unfortunately, in ESGNet, it used the S3PRL as its front end, and it already provided the interface of all those models I mentioned before. So using the S3PRL in ESGNet makes the training more flexible and easier to use. Next, please. And the next part is that we rewrite the data preparing script to make it faster by parallelizing all of the main steps like VD, silence removing, and MSubCC clustering. And we also use the on-the-fly feature extraction to make the data preparation more faster. And we, instead of in FairSync implementation, they use they extract the feature from only one specific layer of the transformer. We extract the features from all the different layers using the weighted sum, and the weight is also trainable in our setup. And so this they have just mentioned is all finished here. And what we're working on is to make the training more stable and efficient. So previously we have tried a lot of different hyperparameters and random seed, but only one of the settings actually works in Librispeech in terms of matching the phone error rate mentioned in the paper. And one of the reasons we think is that it's because of the generator lacking of guidance during the generation. Next, please. So here I have a figure as illustration. So we can see that the real phoneme text is represented as a one-hot matrix, and the output of the generator is the distribution over the phoneme set along the time axis. And when during the generation, each phoneme is generated independently. So we think that the gap between these two representations makes the generator really hard to get updated during the training, and makes it hard to catch up with the discriminator. So that we are adding a guidance to the generator. The guidance can be a language model so that it can force the generator to generate a more reasonable phoneme sequence during the training. And we can also use the word language model instead of phoneme language model in the form of weighted finite state transducer, where the input side is the phoneme sequence and output side is the corresponding word sequence. And we are planning to use the K2 for that because K2 supports differentiable weighted finite state transducer, so that we can do the back propagation in the training. And yeah, so in summary, we re-implemented and supervised ASR training in the ESPNet, and we are trying to make it better and faster. And thanks. So next I'll hand it to Lei.
Thank you very much. Yeah, next for Lei.
Okay. So hi, I'm Lane Berry. I'm a PhD student at the University of Texas at Austin, and I'm going to be talking about incorporating visual grounding into unsupervised ASR. So why do we want to do that? Why do we care about adding visual grounding to unsupervised ASR systems? Well, there are three main motivations. The first one is that it would allow us to bypass phonemization. The current WaveTVEC-U 2.0 ASR paradigm requires the non-parallel text to be phonemized and produces output that are phoneme sequences. So if you want to produce the non-parallel text, or if you want to use the output of the model in any downstream task, you need a pronunciation lexicon. Pronunciation lexicons are difficult and expensive to produce, and they only exist for some of the highest resource languages in the world. On the other hand, visual grounding has been shown to increase dramatically the amount of word level information that's encoded by self-supervised models. So adding visual grounding to these models would allow us to predict word pieces directly rather than predicting phonemes. The second motivation is that it can improve the stability of training these models. One of the major drawbacks of WaveTVEC-U 2.0, the current state of the art for unsupervised ASR, is that its convergence is dependent on the random seed. So if you want to reliably get one or two effectively trained models, you need to start 8 different jobs on 8 GPUs, which multiplies the training cost significantly. On the other hand, a contrastive loss, which we use in visual grounding, is a much more stable loss term than GAN loss. Finally, it can increase the robustness of these models. WaveTVEC-U 2.0 requires the non-parallel text and the speech to come from exactly the same data set, even though they're non-parallel. And semantics are much less impacted by domain shift than form. So the meaning of a word is much more consistent across different data sets than the distribution of that word. So visual grounding would allow us to produce models that are more robust to domain shift. Our first approach to doing unsupervised ASR using visual grounding is to take the cascaded speech clip model that was presented by Ian Shih this morning and adapt it to use alignments to produce, instead of predicting a fixed set of CLS tokens, a fixed set of keywords for the entire utterance, let's predict one CLS, one keyword for each segment in the utterance. That does require us to provide segmentation. So during development, we're using ground truth segmentations. If we were to move this model into like full-scale usage, we would need to transfer to predicted segmentations, for example, from VG Hubert, which introduces some noise. VG Hubert is good at giving you high-quality segmentations for content words, but generally tends to miss function words. So that's a drawback of this model. But in theory, if we can get this model to predict for each sequence of Hubert frames a clip token that best aligns the utterance with an image, then this model will be performing unsupervised ASR despite having not seen any speech text pairs during training. It's only seen image text pairs during the clip training, which is all frozen when it comes to this model, and then seen speech image pairs during this training, which are much easier to collect than speech text. So, can align speech clip recognize words? Well, short answer is no. The generated texts that are produced by this model are not well formed. So for example, for the ground truth caption, a man feeding a giraffe food with his mouth, our model is predicting the caption, shirt hand giving, have animals, pizza taking, giving, have, which is not a meaningful output, right? But there is something interesting going on here, right? We have man is mapping to hand, feeding to giving, giraffe to animals, pizza to food. Those are all like semantically related words, right? So in order to get a sense of how well our model is at least like noticing when it sees the same word during training, we introduced this metric we call consistency score, which is just saying for each ground truth word, we pick the clip token which is most often assigned to that word and divide the number of times it's assigned to that clip token by the total number of times we see the word. If a word appears less than 10 times, we ignore it, we leave it out of this analysis, because a 100% score for a word that appears once or a 50% score for a word that appears twice is not actually meaningful success. So looking at all of the words that appear more than 10 times in Spoken Cocoa, we have an average consistency score of over 61%. And over 31% of those words are getting a score above 75%. Some of those patterns are exactly what we're looking for. So for example, the word kitchen, every time our model sees the word kitchen, it predicts the clip token kitchen. So that one, it's managed to recognize that word. Some of them, it's giving us semantically related words like parked to stop. And then there are some behaviors that are interesting, but not what we're looking for, like bucketing. So any word remotely related to skiing are all being given the clip label skiing. And then there are some things that are just not desirable. So using a default token into for any function word, there's a total of 66 different words that are getting mapped to the token into over 75% of the time. That's not useful, right? So our approach to address this is to add another loss term that pays attention to the form of the output instead of just the semantic content of the output. The way that we do this is we take a pre-trained TinyBERT model with a language modeling head, and we feed the predicted sequences both into the clip text encoder and into that model, and use the perplexity over those sequences as a loss term. The problem that we counter with this is that pre-trained models are trickable. So for example, we have a candidate caption here, which is a valid caption, a man holding a cake that says happy birthday. And we have a caption that was produced by our model, group students enjoying among organized garden outside kitchen together tracks, which is clearly gibberish, right? But both TinyBERT, which we've been using because it's small enough to train efficiently, and the large BERT-based model are giving a significantly lower perplexity score to the gibberish caption generated by our model than they are to a example real valid caption, right? So in order to address this, we need to have the language modeling loss term be adaptable to what our model is learning. And we can do that with adversarial training. One approach is to let the pre-trained TinyBERT be trainable so that it functions as a discriminator. The rest of the model functions as a generator. But we also have all these people at the conference who are doing great work working with Wave2Vec 2.0, which is already doing adversarial training. So instead, we pivoted, and for the second half of this conference, we've been focusing on adding our clip loss term to Wave2Vec 2.0. The first step to make that happen is to replace the Librispeech audio with Spoken Cocoa audio, since the Spoken Cocoa audio is visually grounded, it has associated images for each speech. Secondly, we need to replace phonemization with tokenization so that the outputs are able to be fed into the clip model. When we do that, the frequency of subwords is much lower than the frequency of phonemes, so we need to increase the size and the stride of the kernel. We find that in the Librispeech LM training data, there are 2.81 phonemes for every subword, so we increase by a factor of 3 for both of those. Next, because we have more possible subwords than you have possible phonemes, we use the quantization strategy developed for SpeechClip. So as a reminder, what that is that rather than predicting a distribution over the tokens directly, we predict a token embedding. We normalize all the token embeddings and normalize them to have the same mean and standard distribution as the clip codebook, and then use the cosine similarity with every item in the codebook to get our logits, so that a softmax over those similarity scores is our predicted distribution. Finally, we add our contrastive loss term to the generator training steps and leave the discriminator training steps as is. The first obstacle that we encounter with that is that we find that Wave2Vec 2.0 is incredibly brittle to domain shift. So when we replace the Librispeech audio with spoken Cocoa audio and make no other changes, so we're still predicting phonemes, we're using the optimal hyperparameters found for Wave2Vec-U 2.0 with Librispeech, and we train 12 models for 1 week each. Those models are not improving after the first few epochs, and the phone error rate of the best checkpoints over all of that training are over 100 and nearly 80. So it completely catastrophic failure when you shift the domain even slightly. There is some domain mismatch between Librispeech and spoken Cocoa. So although both data sets consist of read English speech, the Librispeech data is coming from LibriVox audiobooks, while the spoken Cocoa data are read aloud MS Cocoa image captions. And we can see the effect of this domain shift in, for example, the one thing that all of our models seem to consistently learn is to start sentences with the, right? Which initially looks good. But if you look at the distributions of sentence initial the versus sentence initial in these data sets, in spoken Cocoa, you're 16 times more likely to start a caption with than you are with the. Whereas in Librispeech, you're 5 times more likely to start a sentence with the than and so the Wave2Vec-U 2.0 models that are trained with Librispeech LM training data as the non-parallel text and with spoken Cocoa on the audio are quickly learning to hallucinate a the phoneme before they see any utterance initial The second obstacle that we run into is that CLIP is highly brittle to the subword vocabulary size. So the default subword vocabulary size for CLIP is over 49,000 tokens with an extremely long tail of over 38,000 tokens appearing less than 100 times in the Librispeech LM training data and nearly 24,000 tokens appearing less than 10 times. When we reduce that vocabulary size in order to address that long tail and to have a smaller number of potential labels, the retrieval score, so measured in terms of recall at 10, for speech to image retrieval, if we use, or for text to image retrieval, if we use the ground truth caption that is read aloud in the speech, drops from 91% to 75% when we go down to 5,000 tokens, which is still a large set of labels. And if we bring it down to the point that we have less than 100 tokens in the tail, we're down to 26% instead of 91% recall at 10 score. So this is a problem. Despite those problems, we're already seeing that the clip loss stabilizes the training of Wave2Vec-U 2.0. So in these diagrams, the red line is training a Wave2Vec-U 2.0 model with Librispeech LM training data tokenized as the non-parallel text and using the spoken Cocoa audio as our speech, right? And the red line is using just the GAN loss from the original Wave2Vec-U 2.0. The blue line is using both that GAN loss and the clip loss that we're adding to this model. If we look at the LM perplexity for the generated sentences, we can see that the loss for when, or the LM perplexity when we use both GAN and clip loss is both lower and smoother than if we use only the GAN loss. And in fact, when we look at the weighted LM perplexity, which is empirically what we found and what other team members have found to be the most useful for predicting the quality of the final models, the difference in stability is so great that the line for with GAN and clip loss looks nearly flat, right? Because there's so much range we need to have to capture the instability of the training curve with the GAN loss only. But in fact, the GAN and clip loss is consistently dropping this whole time. And even though the version of the GAN loss only has flattened out by the end of this plot, the blue line is dropping consistently the entire way through and is still dropping at the end of this, which is the first 50 epochs. Finally, we look at the vocabulary usage, and this is a problem for both of them, right? So neither of them are getting above 50% usage, which is not good, but adding the clip loss increases the vocabulary usage of the predicted sequences by doubling it. It's an increase of 20% coming from 20%. So even though we have all of these kinks that we're working out in the setting, we're already seeing that adding the clip loss is stabilizing training significantly. So what are the next steps for this project? In the direction of the aligned speech clip model, we're going to add dropout for the segments that have the strongest signal so that it doesn't learn to map a bunch of segments to a default token, so that it has to pay attention to all of the segments, not just the easily recognizable ones like kitchen. We're going to add a pseudo-label reconstruction auxiliary task in order to separate out the segments that are similar semantically but not similar phonetically, to try to get around the bucketing issue that we're observing. And then we're going to add a gradient penalty to stabilize the GAN trading where this large model is the generator. In the Wave2IQ 2.0 direction, where we're adding the clip loss, we're currently working on building a non-parallel text database to use that uses the reserved Spoken Cocoa captions. So the Spoken Cocoa speech is just the first caption for every image, but there's also at least 4 other captions for every image in the Spoken Cocoa dataset that we can use as non-parallel text. So we're both phonemizing and tokenizing those to get around the domain shift issue. We are currently fine-tuning clip to take in a smaller vocabulary size. And finally, because we see so many gains in stability from adding the clip loss, we're working on building a differentiable mapping from phonemes to tokens so that we can add the clip loss to the phoneme predictor version of Wave2IQ 2.0 and hopefully cut the training cost of training a Wave2IQ 2.0 model by 8 if we can get consistently your model's going to converge. So that's this project, and I will pass it off to Jiatong.
Cool. Thank you very much, Lan. And also I will be talking about the last section for our unsupervised ASR part for the using of self-supervised model. So I'm Jiatong Shi from Carnegie Mellon University, just to reintroduce for that. So for the case that after we got the unsupervised ASR model, the direction that I'm thinking about like over the workshop is to how we can better use of it. Of course, we can use it for the ASR because it's quite straightforward task, but we also want to use it as for different scenarios. For example, using it as a self-supervised model because there's no supervision data needed for that. And we can also use it as a segmenter that which we do not need any supervision to that. And we can also really like getting the unsupervised phoneme segmentation from that. And the last one is using it as a connector. So which connecting speech self-supervised model with other self-supervised model. So kind of to do with using this unsupervised ASR as a self-supervised model, what we are doing is something like that. So basically after getting the self-supervised feature from speech, we get to input it into the unsupervised ASR and we get the phoneme posterogram from that and using it as an additional feature to the original self-supervised feature and to the downstream tasks like the phoneme recognition and emotion recognition, query by example, and so on and so forth. So in terms of that, we are testing that on the superb public benchmark. And the case is that we are finding that only adding this unsupervised ASR, which is kind of less than 1% of the parameter size over the Wave2IQ large of its base model, we are kind of getting a very better result given the phoneme recognition, no matter the size, like 100 hours of Librispeech or 10 hours of Librispeech. But we only get similar performance on ASR though, which is a bit sad, but we still can now feel the gap between the Hilbert in the superb public benchmark. But after doing that, we are testing that on the superb hidden set, which we are submitting to the superb community to help us run the model. And in terms of that, we are getting better performances, no matter like Wave2IQ 2 or Hilbert, we are getting better performances on the phoneme recognition and similar performance as well in the ASR. But we also surprisingly found that we can even outperform Hilbert on several other tasks like the emotion recognition, query by example. And in general, our super score, which is introduced by Hongyi last a few 1 hour ago, like basically we can get better performances over the average over 10 tasks over the superb hidden set, which is significant improvements over the Wave2IQ 2 and very slightly improvements over the Hilbert, but we are supposed to be compared with the Wave2IQ 2 because it's a base model over the unsupervised ASR here. So later we're investigating using unsupervised ASR as a segmenter. And this kind of approaches is firstly, we get the unsupervised ASR model and then get the phoneme token from it. Because it's a frame level prediction, we can easily combine the frames with the same predicted phoneme token. So in terms of we then apply a rule-based voice activity detection to refine the segmentation because it is kind of applied as a pre-processing step in the unsupervised ASR training. So after that, we are testing it over like the model of the sequence reduction, which is introduced by Hao and Mengyan for a few hours ago. Like basically, we're like using it as a speech reduction, sequence reduction guidance, contrasted to the Hilbert token we are using to do the segmentation. We can get significant improvements over the phoneme recognition and ASR for that time, but we still kind of have a very large gap between the false aligned, like the boundary there. So which means that we still have a long way to go given the unsupervised segmentation. And for the last part, we are discussing about the unsupervised ASR as a connector. So the basic assumption here is that we're having the pre-trained speech self-supervised model like Hilbert, but it often contains little semantic information, but abundant like the acoustic information. But on the other hand, that basically we have the pre-trained text model, for example, BERT and so on. We can get good language understanding, but cannot be processing speech data directly. So in terms of that, we are like using unsupervised ASR as a connector to connect the model from pre-trained self-supervised model, speech self-supervised model to the pre-trained text model. For here, we have an existing method to connecting those two. Basically, by using the k-means cluster from the self-supervised model from speech, we can get a cluster token, and then using this cluster token as an input to the text self-supervised model, because it's really kind of use the discrete token to as an input for the system. But the domain is still mismatched, given this one is for the acoustic and the other is for the semantic. And what we are doing for the next is to kind of use unsupervised ASR as a connector, which kind of close the domain mismatch because we are converting the domain from acoustic into the semantic. Doing something. Cool. And for the last part, like how we do using this unsupervised ASR as a connector here is that after we getting the unsupervised ASR output, we are like concatenating the feature from the unsupervised ASR, the self-supervised feature from speech, and the self-supervised feature from the text, so that we can get additional feature space over the text model of the language understanding. And we are testing it mainly focusing on the understanding tests, like including the intent classification and speech translation here. So here we are reporting our result in current setup. So basically we have the speech self-supervised model as a wave-to-vector large, which is trained on LibRLAD 6,000 pre-trained model. And we are like using the connector, which has two options. Firstly is the k-means cluster that we are having the pre-trained k-means from the text NLP from Farsight. And we are then using the unsupervised ASR to generate the unsupervised token ID to connect the model from speech and text. And we're also using the pre-trained text model, which is a phoneme by T5 used at the default setting, because we are output phoneme token from the unsupervised ASR to connect both. And the later one, we have the training options of two. Like first one is that we have the fixed feature extractor. So basically we fix the feature and do not do the fine tuning and performing it on the internet classification on the super public benchmark. And the later we are doing the fine tuning of the feature extractor and test it on the slurp with the ESNet recipe. So in terms of that, we are showing the results kind of compared the k-means option and the UASR option. So here we can clearly find that we can get better performances using unsupervised ASR as a connector. And it turns out that the k-means method cannot be function well without the pre-training, without the fine tuning, but we could get significantly better result over the unsupervised ASR in that case. But we also can outperform the original baseline and as well as the k-means method by doing the fine tuning over the training. So the final take-home messages will be something like that. So the unsupervised ASR as a self-supervised model can get better performances in phoneme recognition, as well as some improvements on other tasks. And the unsupervised ASR as a segmenter will have a better quality than Hilbert cluster-based segmentation. And for unsupervised ASR as a connector, we can connect speech self-supervised model and text pre-trained model, and better result could be achieved either with or without the fine-tuning here. And this is the end of my section. We'll be handing the mic to Leo.
Hi, everyone. So I'm Leo, and I would like to give an introduction on L3PRL and its recent upgrade in JSOT. So I'm collaborating with Andy, Henry, and Haibin, and Liang Zheng. So SRPRL stands for the self-supervised pre-training and representation learning, created by NZ and I, collaborating with lots of researchers and under the supervision of Professor Hong Yi. So we have three major functionalities: the pre-training, pre-trained model collection, and then downstream benchmarking. For the pre-training part, we can pre-train some classic methods like Mockingjay, Terra, APC. And for our pre-trained model collection, we have a comprehensive library for all kinds of research related to the self-supervised learning in speech, so that we unify the retrieval and IO interface for all the SSL models, that we can extract all the hidden stats for them. And for a downstream benchmarking, that we support the Superb benchmark and the Superb SG benchmark, that in total there are 15 tasks. So our role in the JSO workshop is that we are providing the continuous support for all the pre-training team, that they are developing new techniques like compression and robustness and the feature enhancement. And then we get feature requests and bug reports, and we are continuous to add the new features. So for a feature request, it's like, how can you change the corpus, or you can change the probing model, or that you can, how to benchmark compared to the latest SOTA like the XLSR, or for a bug report that people are facing the basic installation issues, and we are also trying to fix that. So our major updates in JSON is like that we add lots more new upstream models, and we make all the upstream collection models more stable. And for a downstream benchmarking pipeline, we make them modularized and customizable so that people can easily adapt to new experimental setting. And also it is because of this new flexibility that we can easily expand the horizon of SRPRL into the sound domain, that's for the sound self-supervised learning and the sound related task. So for a more upstream model, that in the original Superb, that we support the models in gray. And now during the JSO, that we add lots of new models in the orange, that you can use them in the SRPRL. So for a more stable upstream, that we have the SSO features, you can easily connect. It already be connected with the ESP.NET. You can use them in the ESP.NET ASR, SLU, and the ST task. And to have a more stable support for ESP.NET, we remove all the basic dependencies, and also we add the numerical task for all the upstream model for a forward and backward task, so that you can expect the exactly same behavior across the SRPRL versions. So for a downstream benchmarking pipeline, that originally in our recipe, that the recipe is tied to a specific model or a specific corpus. And so that every time you want to slightly change the experimental setting, you require the library code change. And this means that the user needs to trace the library code, which is time consuming. So during the workshop there, we define some model API so that people can customize their own model and easily switch between different tasks. And also we're following PALD to define some task data format so people can easily process their own corpus to a standardized data format and use our existing task benchmarking pipeline. So we are like refactoring and rebuilding lots of things in the new code base, but we guarantee that it is backward compatible and get a comparable benchmark results between the new and old version, that we get a very insignificant relative change between the code base. So with a new code base, that we can easily like plug in a new corpora, plug in a new upstream model, plug in a new downstream model, and we get the new recipes. So we are thinking that besides supporting other teams for a new feature request, what can we try more during the JSO workshop? So the story is like, we already have a quite complete ecosystem for the speech self-supervised learning. Like we have a speech pre-training model and also the benchmarking pipeline, like for the Superb task. So the story is like, what about other sounds? Like we have the animal sounds, we have the environmental sounds and music and instruments. Okay, so the story is like, there are lots of sounds out there, tons of sounds that which actually you can expect that the speech pre-trained model actually know very, very little about that. So the fact is, actually there is also another ecosystem for the sound domain. There's a here benchmark that they define the 19 tasks for the sound event detection, recognition, music genre classification, music transcription, and there are also the sound pre-trained model like the SSAST from MIT, Boyle Audio from NTT, and the COLA from Google. So the question is like,
in the past, that we have people working on speech and people working on sound, and usually we can use just local mail spectrogram as a standard for lots of tasks, even for the music, like the music transcription in the sound or the ASR in the ASR, because it is stable. It is stable that you can expect that you can always get some kind of decent performance across all kinds of waveforms. But how about, do we have a single neural representation model that it is stable enough that we can, for any waveform, we can always expect the decent performance for all kinds of this kind of task, like a human ear, you can always process all kinds of waveforms. So toward this kind of universal audio pre-training, that we need a handy evaluation code base for all kinds of audio and waveforms, and we already have lots of evaluation tools for speech in adversarial, including the baseline models and the downstream evaluation pipeline. So to expand to the sound domain, that there are 19 here tasks in a here benchmark. It seems a lot, but actually they share the basically the same machine learning training logic compared to the one in the super benchmark, like just the classification or the cross validation, or like the frame label, multi-label classification between the speaker diarization and the music transcription. So actually, we can very easily adapt all the here benchmark by just changing the corpus, changing the downstream model, and we can easily support all the 19 tasks with the exact same benchmark result during the JSON workshop. So now that you have the speech pre-trained model in adversarial, you also have the sound pre-trained model in adversarial, and you can benchmark all of them on the super benchmark, and you can benchmark all of them on the here benchmark, and you can do the cross comparison. So here is also to verify the correctness that we also compare our benchmark numbers with the official one with some representative tasks, and of course they should be correct. And also that in the adversarial, we have the flexible option on how to utilize the upstream model. You can extract a single layer, or you can weight some all the hidden set, or you can fine-tune the pre-trained model. And after we follow the superb way to do the weighted sum, we actually get quite significant improvement upon the number reported on the here benchmark. So that, yeah, okay. So also that, of course, we need to do some cross comparison. Is that for a representative one, that Web2 2 for a speech and the recent SOTA, the audio for a sound. And of course, that we can expect that the speech model currently and the sound model will just only work on sound. And when you have a domain mismatch, there will be a significant performance drop. And also that there are some researchers now starting to think about how to combine the both research direction into a single model, like the SSAST and the MAEAST. They pre-trained their model both on the Librispeech and audio set. So after we benchmark the MAEAST on the here benchmark, that we found that actually they can kind of like getting the new SOTA on the benchmark for the music transcription and the sound event detection. However, for other tasks like the SID in Superb or the sound event recognition on the here benchmark, they're still not quite ideal. So the story is, it's different from the story in Superb benchmark. Like nowadays, you just get a single model WebLM and it just gets SOTA on all the speech tasks, or or the XLSR something. But when you consider a broader range of waveforms of audio, actually, they are still not stable enough to represent all kinds of waveforms and audio. So as a takeaway, that we have a new modularized and customizable code base that we can quickly adapt to lots of different settings, even for the sound domain, and we quickly adapt all the here benchmark tasks during the JSON. And that we have more and stabler upstream that we are already scheduled to integrate with ESPN after the JSON, that we are more, yeah. And the third one is that we are one step closer on unifying the SSL evaluation for the representation on all kinds of waveforms. So we have the new code base for the speech SSL and sound SSL. And you can do the cross comparison. Yeah, this is my part. Thank you, everyone.
I do not plan to go through the conclusion slides, so I think we can start the Q&A session. And we have 10 minutes left for question and answer. And so let me ask any question from people online? Or any question from the audience here?
Go ahead and finish it. Okay.
Okay.
Quick question regarding the using the algorithm learning model for segmentation tasks. So can you give me more detail how do you perform segmentation on which level from segmentation? Is on word level, phone level? In terms of measurement, how do you give me insight? So the model doesn't perform good in terms of the time alignment or is that the word or subwords, and is the model generating the blank symbol? Do you have to rely on decoder? How do you do that?
Yeah, you probably you can come to the stage and repeat the question and answer it. Okay.
Yes. So I think the question here is that how we can process with the segmentation like on word level, like either it's on phoneme or word or subword or something like that. And also like what's the detail, like is there like blank label in that or something? So the short answer is that we're quite simple, like we are doing on the phoneme level because unsupervised ASR is doing on the phoneme level. So but here like in the unsupervised ASR kind of framework is doing like a CTC like kind of loss, but it's not exactly the same, but it's quite similar. So in that case, like they will be having the compression over the tokens. But in that, the difference from is kind of different from the CTC in terms of it do not have the blank token. So basically, it will be just have the phoneme token directly, and it will be compressed similar to the same phoneme token into one in terms of the segmentation. So if we want to get the segmentation from that, the short answer is quite simple. We firstly do the argmax over the time frame, and which is 60 milliseconds over the frame shift. And in terms of that, we are combining those phoneme which having the similar like exactly the same code, like the same phoneme, and so that will be form a segmentation over that kind of phoneme style. Cool.
Okay. Any question from the audience? Yeah.
Okay. Is there any limitation? Because when I'm thinking about like the fact of gathering everything for all the tasks, basically, I think the single representation for everything. And would there be like some kind of problem? I'm just thinking that maybe you want just to have a representation that keep the speaker information, but discard actually the semantic, the phonetic information, and vice versa. So I'm just a little bit curious about your take here. Is it to tie it together everything?
So I know your question. You are thinking about why we want to have a universal model. Is it possible to have a model for a specific task? So in my point of view, the ultimate self-supervised model is look like this. They have some common part to deal with to extract some common feature for speech representation, but they also have some specific part for specific tasks. So as you know, in Super Benchmark, you submit one model. However, we allow you to choose different feature for different model. So when you submit your model, you can specify that for this task, I want to use this feature. For another task, we want to select different feature. Of course, now usually people just use all the feature. But in my point of view, in the future, if you want to get very good performance on Super Board, probably you need a model like this. The model has different branches. So you have some common root, then spread different branches to different tasks. Then when you use this model in all the different tasks, you have to know which task you want to use and select the correct branch to get the best performance. So this is my ultimate idea about self-supervised model. So any question from, yes?
Yeah, I want to follow up that question. So you show that you want to build a universal model not only for speaker recognition tasks, ASR tasks, but also for some detection or instrument detection tasks. what is the motivation of having a universal model that works for both speech and sound? What is one thing of that? For example, for some instruments, you should pay attention to the high frequency range. For the speech, you probably pay more attention on the low frequency. But why having the universal model? Do you have any specific you want to tackle leveraging this universal model?
I found Leo, do you want to answer this question? You can come to the stage and repeat the question.
Yes, I believe it's a very good question. And I believe it is because that usually our speech, when we are having a recording outside there, we won't only have speech, and we always have speech with the environmental sound and this kind of mixture. And usually, like from the robustness team, usually we know that you can easily don't understand what is happening when it is augmented with noise. And current approach is like, okay, I just don't want our audio part. We don't want the sound part, and I just ignore them. But then we create a model that it only knows about speech, and it then don't know when I'm talking to Hongyi and there's a cat meowing beside. Actually, the model don't know what's happening beside there. And also, this is considering when I have a conversation with Hongyi at the beside the road. And another scenario is that for like the singing voice, and you consider a song, there will be the instrument, and there will also be the singing voice. People are having some lyrics, and they also have the piano sound and the violin behind that, and they are all mixed together. And then it becomes very hard when your model just only understand one kind of sound when they are mixed together, very complicated.
Yes.
Just follow up on that question. I mean, it seems like you're conflating two things. One is robustness, noise, various times, whatever. The other is providing a label. If you don't need the label, why both parameters? Why not train with the noise and learn to ignore it? But why do you need to say, oh, this is a singing or something?
I think I want to answer more about that question. It's about, I think it's like you always can get good performance. Like if I only care about ASR, like before the self-supervised pre-training only care about ASR. So you can actually do lots of trick just tuning for ASR. And also for the speaker verification, I can do lots of trick just tune the pre-training for the speaker verification. But I think the problem is that doing this kind of pre-training is requires very huge computation resource and lots of efforts. And the benefit of this kind of pre-training is that once we do pre-training and they acquire the general knowledge, and they can easily adapt to all kinds of tasks. Yeah.
Paula, want to say something?
Yeah, I just want to elaborate a little bit more on what Leo is saying. So when I think I also had this question when I arrived to this team, and the truth is that I found it kind of surprising that a unique model can work for each of these tasks in a very simple way. Because I was also asking about the downstream task to Leo and to some other members of the team. And it's just like a single layer plus something else, and that's a classifier. And that's it, for example, for speaker ID or even for phone recognition, that's the ones that I remember. So if you want to do something a little bit more fancy, or if you want to really tackle speaker ID, you can even do something else. But you already have something that is like a general model that can be very useful, and it can work for the different tasks, for the different tasks in a certain level. So I think that is one of the main important things of all this all this work. And you can also then fine tune a little bit more and really tackle your desired task. I think that is also what we want, or what we are also doing here at Hopkins, getting some of these models already that they are already pre-trained and fine-tuned, and these general models that are already working for the different tasks, and fine-tuned, for example, for speaker ID and other tasks with a more complex downstream code, let's say.
Oh, yeah, can I just add to that, like from the grounding perspective, that people talk about their environment, right? And the other sounds in the audio are part of the environment. So like, maybe this is a bit of a contrived example, but like if I am going to meet my friend to get dinner, right? And I arrive and I'm complaining about the traffic, and then the song changes in the background and I go, oh, what a jam, right? The correct ASR output is JMB, right? If I'm still talking about the traffic. But if it can notice that something has changed in the background noise, it's got music detection that tells it, oh, this is a different music than it was before, then it might be able to say, oh, the correct output is actually JAM. I'm talking about the music now because something changed in my environment. So I do think that like in the limit, having knowledge about the environment does help ASR, and being able to handle sounds that are like mixed into the same audio track that are both speech and environmental sounds can improve the speech recognition. That's my take from the grounding perspective.
Your response goes back to this comment that so we are talking about robustness and being able to distinguish speech even in the presence of background noise or music or whatever. But we're talking about two ends of spectrum here. So you have a Huber that is trained only using speech, that hasn't seen the characteristics, the frequency profile of birds singing or different instruments, right? You can have a Huber model that is trained, that is also pre-trained on music data, instruments, sounds, environmental sounds, birds singing, things like that. So these are two ends of, and then you can fine-tune those for their respective downstreams, right? Or you can also have a middle ground where you combine instrumental sounds, birds singing, music. Things like that with speech, and then train one more, but you haven't done that, right? You don't have a Huber that is trained with speech plus other sounds.
Yes.
So I think this question is more like, why should we, when we can train a Huber that is good in terms of capturing and representing sounds other than speech, music, birds, why should I just stick to a Huber that is only trained with speech?
Yes. And I think that this question is also related to how Professor Hongyi answer is like, or no, I'm just trying to say that if you just care about speech, then I can always train a model with just speech. And I only care about music, I only pre-train the model with music. I only care about environment sound, I pre-train the model with environment sound. I only care about speaker, I pre-train the model with speaker. So every time you want to deal with the specific kind of data, you can pre-train a specific model for that. But we cannot pre-train that. Like you don't have the resource, I don't have the resource. So when we want to represent one kind of data, like this kind of data is waveforms, and it is already like
you have lots of sounds that are access to data sets resources that are not speech, right?
Yeah.
So you can combine that with Librispeech or whatever
you're
using, and train the whole model with in an unsupervised fashion, right? So you can do that, right?
Yeah.
Yeah.
So you actually have some result about that, right?
Oh yeah. Someone do that.
Based on an existing model, there's an existing model trained by both speech and sound. I know now the question is, if we already know that we are dealing with the speech processing test, adding sound as the pre-trained data, is it helpful or not?
Oh no, I don't think that. I don't think that if I mix the sound and speech together, pre-trained model will definitely help the speech processing, because I'm here. The target is not caring about how to improve the speech processing with other sounds. It's about how I can have a
spend lots of effort and pre-train just a single model, and it is generally applicable for lots of different things. Okay. So yeah, okay.
Yeah. Sorry about it. We can bring the topic to the lunch.
Okay. Right, no, this is a good discussion. I
Yes.
think it's good that the discussion started. Let's continue this.
Yeah,
over
yeah, yeah.
lunch.
And I have to say, because our presentation is end, so we are very relaxed. So
yes,
we will be very available today and tomorrow. We are always full around, so feel free to talk to us.
Right. So thanks to all the speakers. And remember, we're going to be back at 2 o'clock. So please, we have an hour and 10 minutes for lunch. Let's be efficient.